probably the biggest lesson we have right now. The biggest one in the chapter is this lesson. It's going to take a long time. There's a lot of good stuff in here. And as I was introing this to y'all, we're going to talk about just two things, lines and planes. The formulas are very easy. They are very similar. And as I told you, some of you, many of you, you're going to make a mistake between the formulas of lines and planes. It's going to happen. Just be very careful when you're going through them so you later on, when you're done with the homework, you don't make those mistakes anymore. So we'll talk about those formulas. Honestly, it's probably enough to talk about the formulas and, hey, here's how it works. But we're going to spend the vast majority talking about the harder examples, like how do you use this stuff. We'll make it through lines pretty quickly, and then we'll talk about planes, and then, as I said, the last thing we're going to do is talk about how to find the distance between a lot of these different things, a point in a plane, a point in a line, parallel planes, skew lines, what skew line even means. And how it all starts is really just an understanding, how would we define a line? How would we do that? Now let's start here. What do you need in order to define a unique line?
2 points.
You need 2 points. Okay, great. In 2 dimensions, and that's still true. In 2 dimensions, we go, well, you need 2 points, or you need 1 point, and good. Well, in 3D, we lose the slope idea, but we gain the vector idea. So in 3D, we go, yeah, you could do this with 2 points. Or, just like the point slope thing, we could do it with 1 point and a vector that has the same direction. Okay, same direction. What's that mean? Same unit vector, or it means that they are parallel. So we can do it with a point and a vector that's going in the same direction, just parallel to that line. That's the idea on how we're going to build the formula for a line. We're going to build it. Okay, we're going to do it from scratch so you actually understand where everything's coming from. So let's write just a couple things out. In order to determine a line in space, you need a point and you need a vector in the same direction of that line. So you need to know where it's headed. That's the idea. So we could do this with 2 points because, hey, between any 2 points you can find a vector, right? Just like between any 2 points you can find a slope. So the idea of a vector takes the idea of a slope and pushes it to 3D. That is what's happening. Head nod if you're okay with the idea behind it. Let me draw you a little picture. Then we're gonna do everything. We'll do some examples. Basically, here's the idea. It says, hey, in 3D, if I wanted to find a line through random point, all I need is that point, that specific point. So I want to go through, I don't know what point that is, but I want to go through that point, and I want it in that direction. Well, that's all I really need. All I need is what direction I'm headed and what point I'm going through. And if I can do that, then I know the line is going to be parallel to that vector. That's the whole idea. You have a point, find a vector of the direction that you want to go in, and then we can build this formula from it. So keep this picture in your mind as we're coming up with the formula, and you're going to be a lot better off for it. So this really acts like point slope. It's just we have now point vector. Notice I already said it, but notice if I give you 2 points, you can always find the vector between those 2 points. Does that make sense? So what 2 things do we need to make a line? Now, point and vector. Direction vector. That's all we need. The vector of the direction. So let's start building with this. So since the line is going to be parallel to the vector, so I'm going to write all this stuff out. So the line is going to be parallel to the vector. Just for fun. Hey, what do you know about things that are parallel? And I know they have the same unit vector, but I want the other one. What they are? Someone said it. Say it louder.
Scalar.
They're scalar multiples. Oh, so okay. So stick with me here. This is the whole big deal. Okay, and then everything flows from it algebraically. It's really easy. The vector of that line and the direction vector are parallel vectors. Does that make sense? If they are parallel vectors, the vector of the line has to be a scalar multiple of the direction vector. That's what we're going to call this thing, the direction vector. Well, if they're scalar multiples, let's just give it like a little letter to represent the scalar. Let's call it t. Y, you'll see y. I know it's I've talked it 3 times now, but I want to make sure you get this because from this flows everything else, okay? Do you understand the idea? We need a point. There's our point. We need a vector that says I'm headed in this direction. There's our vector. If we have the line in the same direction as that vector, direction vector, then the line is parallel to the vector heading out if you're okay with that. Any vector on this line is going to be parallel to this particular vector that we're saying is in the same direction as the line. What that means is any vector on here, the vector of the line, is going to be a scalar multiple of this vector. And that's all I'm saying. The vector on this line, or of this line, just any vector in there, is going to be a scalar multiple of this direction vector. That's the idea. Head nod if you're okay with that one. We also said something else. We said, given any 2 points on a line, you can always find the vector between them. Do you remember doing that? Just subtract the values of x, subtract the values of y, subtract the values of z, get a position vector. Pretty not so bad. So let's talk about this. So given a point, we call the actual points the p sub 0 like a specified point on a line. And any other point. So if I give us a point, just a specified point 3, 1, 2, and any other point, x, y, z, so we're letting that float, but it's any point on that line. Do you guys understand what I'm talking about? Where we're going to get our variable is from this x, y, z. So I have a point on the line, and any other point, it just has to be on the line. I don't care what it is. We can always find a vector between this point and this point. We can always find that vector. And it's going to be a vector on that line because these 2 points are on that line. It's got to be there. So the vector of the line, that's that little L there. So the vector of the line is going to be, let's call it the same. It's going to be the same as the vector between p sub 0 and p, any other point. We do a 20-second recap because then it's pure algebra. You guys, we already talked about it, but you get the idea. This line, hey, it's parallel to the vector. If it's parallel to the vector, any vector on that line is a scalar multiple of the direction vector. That's the idea. More than that, if I give you a point, we can always find the vector of that line between a point and any other one. Between a point and any other one. And in fact, the way that we do that, this minus this, this minus this, this minus this is how we always find the vector between 2 points. So the vector of the line, if these 2 points are on that line, says, well, yeah, just subtract them. And that's what we use to represent the vector of that line. Are you sure you're okay with this? We got one more thing. We do have to identify this direction vector, so the direction of our line. So these things are parallel here. We call this the direction vector, and A, B, and C, the components of the direction vector, we call those direction numbers. Why? Because they give us the direction. That's why. Of the X, Y, and Z. Okay, we're almost done. It doesn't even look like we're almost done, but we're almost done. Here's the whole punchline of this. I'm going to do it over here. You guys have it written down? I get 2 points on the line. I can always find the vector between them. In fact, here it is. Here's the whole point. I know that if this vector is in the same direction as my line, that they are parallel. If they are parallel, then they are scalar multiples. If they're scalar multiples, let's use t as the scalar, then here's what I know. The direction of my line that's the vector of my line has to be this. We literally have it right here. Here's the vector of my line. Here's the vector of my line. I did it, man. There's 2 points. It's fractal. That's the vector of my line. I know they're parallel. Therefore, I know that the vector of my line is a scalar multiple of the direction vector. What's telling me the direction of my line? It's almost trivial. It's saying, yeah, they're parallel. You're going to just multiply by whatever number it takes to get you from this one. Multiply by a scalar. It's just going to move your vector somewhere. It's not going to alter the direction. It's going to move it so that it matches up with that line. That's what this says. That's all it says. Show if hands feel okay with what it says. And now comes the algebra. Since we found that vector, and since we gave this one some letters, what are the letters for that vector? What are those? Yeah, those are my direction numbers because that's my direction vector. See if you can make the jump. Do you guys see where these things are coming from? Hello, yes, no? Yes. What vector is this? Any vector on the line. What's this? Good. That's this one saying, hey, I'm headed in this direction. It's just a position vector, which is nice to deal with. But you know what? This vector has to be a scalar multiple of this vector because they're in the same direction. That means that they are parallel. I'm just kind of moving it somewhere so it matches up through some point. That's essentially what I'm doing. Let's do a couple things here. Let's distribute a scalar, because I can. It's not a dot product, it's just a number. Awesome. What do you have here? You got a vector. Equal to a vector. If vectors are equal, their components must be equal. I hope you're not getting bored. It's not hard, but it's important you see where it comes from. I don't want to just give it to you, because otherwise I'm going to give you the formula and go, what are these pieces? That's silly. You guys okay with that one? Now, the way that equations of lines and such usually work is we like to solve for variables. Is that a variable? No. What is it? Come on, put it. What is that? What is that? The x coordinate of that specific point that I have to give you. Does that make sense? Or you have to be able to find. It's a point. It's the x coordinate point. That's the y coordinate. That's the z coordinate. What is the a and the b and the c? Where is that coming from? Not necessarily a unit vector. In fact, I don't want you to think unit vector. The direction vector does not have to be a unit vector. These are those variables. Let's solve for the variables. take about 10 seconds and let's see if we can absorb this, okay? What I want to do, what I want you to do in your head is work your way through this. Think about, okay, I have a line and it's the same direction as some other position vector, no problem. That means they're parallel. Parallel means scalar multiples. Any vector between 2 points, easy to do, just subtract them. We got a vector. If this vector is in the same direction as this vector, then this equals a scalar multiple of this. That's this. Let's drop it down. Here's the vector we found between 2 points, one specific and one just somewhere else on the line. This one was given to you as ABC. Distribute, do all this stuff, work it down. This is the equation of a line in 3 dimensions. Why does it look weird? You know why we use the t? Do you remember Calculus 2? Remember section 10.3? 10.2? When you did parametric equations?
Yeah.
In 3D, lines are parametric equations. They have to be. Because we have to tell it, okay, at a certain time, same t, you're taking a vector, ABC, and you're pushing it up until it goes through, or down, until it goes through that point. That is what is happening. That's the idea. You're multiplying by a number to push the vector up until it goes through the point. It's kind of cool, right? And you have to do that with parametric. So this right here, this is the parametric equation for a line. In 3 space, R3, 3D. By the way, if you cover that up, you might have seen that in 2D, in parametric. You might have seen this stuff before. How about this one, though? How about this? Firstly, what is t going from? What's the interval of t? What is it? If you have a line, how far do lines go? Forever. So this parameter, this t, goes typically from negative infinity to positive infinity unless you have problems with your t, like domain issues or something, or you stop it. You say, I'm just talking about this interval. So typically, this t goes forever. Now here's my next question. Can you take, since it's the same t, can you solve each of these for t?
Yes.
Let's try that. I'm going to do it real quick like. So t equals x minus x0 over a. You could actually do it from here. This is probably easier. Solve for t here, here, and here. One more little step here. Notice it's the same t. So if this is the same t that we have solved for, combine all this stuff down. That's weird. Does it make sense on how we get that?
Yeah.
Come on, look at the board here real quick. Does it make sense on how we get to that? If we can solve for t, solve for t, solve for t, then these things have to be equal. This is a different way to write the same thing. So there's 2 ways to write the equation of a line. 2 ways for us. This one, which I actually like this one a whole lot. This one, this is the parametric equation for a line because you're given the parameter t. That's the only variable that you have is that t. Plug in t gives you x coordinate. Plug in t gives you y coordinate. Plug in t gives you z coordinate. That's the parameter. Or if you solve for t, you have this form. This is called the symmetric equation of a line. Either one, we're going to use both. It's very much like the vector notation, I, J, K, or vector brackets, same junk, okay? The real things I want you to know is what the pieces do, all right? So we're going to write down what this is, and then we'll talk about what all these things are. These 2 things say the same thing. I'm sorry, I missed it. These two things say the same thing. I want you to use them universally. Firstly, I want you to see what goes on. Do you understand that these are equivalent? This one and this one's equivalent. We got the parametric or we got the symmetric. They say the same thing. What they say is, hey, what two things do you need to make the equation of a line in 3D? What two things? A point and a direction vector. Does this have a point and a direction vector in it? So this is for, hey, if I give you a point, now wait a minute, let's see if you're really paying attention. What's the point? Some of you guys are wondering that right now. What is the point? Man, what is the point? In both of these, this or this, what's the point? Exactly what we started with, the given point. So this works for any point. You need a point, you need a vector. Point and direction vector. And, oh my gosh, what's the vector? Vector ABC. Now, let's see, 20 minutes? Talk for 20 minutes about the equation of line. Is it super hard? No, it's not. It's really, really easy. But I want you to get where it comes from. I could have started the class right here and said, this is the equation of a line. Start with a point, x0, y0, you just put it here. And you take a vector in the same direction and you put it here. And you know what, you can do it that way. But I want you to understand the idea of why this is the way it is. Have I explained it well enough for you to understand where it comes from? You're taking a direction vector, you're pushing it up by multiplying by a scalar multiple until it actually goes through your point. That's what you're doing. You go, okay, well, how do I do that? Take the point, take the vector, add some crap to it until it hits the point. That's what we're doing, really. We're taking a vector, multiplying, scalar, raising it, and going through that point. That's the idea. Didn't know if you're okay with the idea. Now, how we use it, it's honestly really easy. As long as you're given the two things you need. If I give you a point and a vector, you can fill out either one of these things. X sub 0, y sub 0, or x sub 0, y sub 0, z sub 0, and then the direction numbers, A, B, C, in the same order. It's really nice. X goes with X, and the X coordinate of the point goes with X. The X component of the vector goes with X. Please just don't get these confused. It's really easy for students to be given this thing that has three numbers, and this thing that has three numbers, and put them in all the wrong spots. And put this here, and then you don't have the same thing. Does that make sense? Be careful on what these are. Also, what's really cool, anytime I give you one of these lines, and I say, hey, can you find the vector that's parallel to that line? Can you find a vector that's parallel to this? Yeah, as long as you have A, B, and C, you automatically have the vector. Can you find a point on the line? Yeah, automatically you have a point on the line. It's pretty cool. It literally gives us the two things we need to make the equation of line. Now, let's practice some, because I know I've probably bored the crap out of you just right now with all that. I hope I didn't. I wanted you to understand it. You know what? Actually, I'm going to write a couple notes before I do that. I know I'm going to forget if I don't do this. I want you to know that if a direction number, what's a direction number? X, 0, Y sub 0, Z sub 0, or ABC? What are direction numbers? Quickly. If one of those is 0, it's possible. You lose the equation because you have this undefined thing. If one of those is 0, so here or here or here, if one of those is 0, then what that means is that the line is actually bound in a plane. If a direction number is 0, your line is actually in a plane that's parallel to the YZ axis, the XZ axis, or the XY axis. I'm going to write that out here real quick. specifically? Let's just say that A is 0, okay? So 0 means this piece is 0. 0 times a number, I don't care what it is 0. So what that means is that x would equal x sub 0. You can do it here, but this is easier. X would equal x sub 0. Does that make sense to you? What this means here, ladies and gentlemen, please focus. I know there's not a lot of numbers, okay? But that's going to be a number. It's going to be a point like 3 or negative 5. Does it make sense? What this means, if that number is 0, the line is going to lie in the x equals x sub 0 plane. So if that's 3, it's going to lie in that plane. Remember drawing planes? The plane would go through that x equal 3 or x sub 0, whatever that is. It's going to lie in that plane somewhere. It's actually kind of 2D. It'll be parallel to the YZ plane. That's what would happen here. Last little note. How would you tell two lines are parallel in 2D? Not a trick question. You should know this.
Never cross.
They never cross. Okay, yeah, that's true. How do you tell if they're parallel though? Like really easy. You got y equals mx plus b. How do you tell if the two lines are parallel? Same slope. Do we have slope in 3D? Not yet. What do we have in 3D? How do you tell that two lines will be parallel in 3D?
Same direction.
Same direction, same unit vector, or scalar multiples. If their direction vectors are scalar multiples. Just like we always check for parallel vectors. Remember talking about parallel vectors, right? Same stuff, man. Look at the vector of the lines. Hey, if they're scalar multiples, the lines are parallel. Does that make sense to you? That's how we always check. So two lines are parallel if their direction vectors are parallel. Lines are parallel. If the direction vectors are parallel. Okay, now pop quiz knows. How do you tell when two vectors are parallel? Do you use a cross product? Do you find unit vectors, or do you look for scalar multiples?
Scalar multiples.
Because that's so freaking fast. Okay, do that. So what this means is, hey, yeah, two lines are parallel if the direction vectors of those lines are scalar multiples. If that makes sense. This should be the only thing in the world you ever do to figure out whether two vectors are parallel. Look for scalar multiples because it's fast. It's really nice. Now we're ready, man. Now we're ready to go. We've talked about a lot of stuff. I need to make sure it makes absolute sense. Show of hands if you feel okay with what we've talked about. Now I know it's hopefully it's not vague, but it's not concrete yet because we haven't done much. Let's start that right now. Please don't zone out as I'm going through these examples, because like halfway through a lot of these examples, I start teaching you other things. Like, oh, here's a note. Watch what happens. All right. So if we just kind of gloss this over, you're going to miss some things. So please stick with me here. Number one thing, y'all need to know, what do you need in order to find the equation of line in 3D? What do you need? Point and a vector. Point and a vector. Point and direction vector. Do we have a point?
Yes.
In fact, we get 2 points. Pick one, doesn't matter which one. Do we have a vector?
No.
How do we find a vector? Just like we need 2 points to find the slope, we need 2 points to find a vector. Same stuff. Let's find the vector between PQ. Go ahead and do that. Did you find the direction vector for this line? If you're like, wait a minute, that's a position vector. Yeah, that's the whole point. That's why we're taking this position vector, multiplying by scalar, because we never find a vector between 2 points. It's automatically a position vector. That's why the picture was relevant earlier. It said, yeah, you get this vector starting at the origin. Why? Because every time we find a vector, it moves it there. And then we have to have that scalar multiple to move it through the point. That's the plan here. So when you did this, how much do you get?
2. 7 halves. Negative 5.
I'm going to believe you. Can I get a triple check on that, though? Perfect. All right. See how much I believed you. Just kidding. It just happens, you know. So to find the equation of a line, we need a point. What point are you going to use? Doesn't matter. Pick one. Doesn't matter. Let's pick P, just so we all have the same thing on our notes here. Let's pick P. So I'll pick the point. And we need a vector. We already got one. We have it right now. Oh, but wait a second. I want you to think this is one of those little things, okay? One of the little things I'm going to teach you right here. Don't write anything down. Change it. You guys okay with the idea we need a point and a vector? We got a point, we need a vector. We have a vector. You can use that vector. But here's the whole point about that vector. It doesn't have to be a unit vector. It doesn't even have to be the vector you find right there. It just has to be the vector in the same direction. So make it nice on yourself. If you got like those 1/2s here, you go, no, dude, I don't, that's silly. We can multiply any vector by a scalar multiple, that's a number, and get a vector in the same direction, right? All this thing says it's in the direction we want. Multiply by whatever you want. I would multiply all this stuff by 2. Is it going to be in the same direction? Yes. Is it going to be the same vector? No, who cares? It's in the same direction. It's just a direction vector. So, long story made short, if you have fractions, oh goodness, multiply by the LCD of your fractions. That's nice, okay? It gets rid of fractions. If you have huge vector numbers here, huge direction numbers, you can divide them all by a common denominator, the greatest common factor. You can change the sign, you multiply by negatives. You can basically do whatever you want. Please make this mental note. I know some of you guys are writing, but stop. You can always do this unless you are talking about distances. Because distance is built into these numbers, okay? So as soon as we start talking about distances, can we do this junk? No. But if we're not, if we're just talking about direction, go for it. So I would for sure multiply this by 2 and change my vector. Now, what's easier? That's easier. That's a lot easier. How about this one? Can I do that to the point? No, because the point is the actual spot in space. Okay, unfortunately, you can't do that. But you can do this with the vector. So modify your vectors as long as you keep the same direction, and that means multiply by whatever number you want, as long as it's a scalar, and you're good to go. Should fans feel okay with that one? Now I want to see if we can do this together. I'm going to write the equation of the line. I'm going to start with the parametric equation. Literally all you do, put your x, y, and z coordinates, put your direction numbers in the appropriate order. We need a x coordinate, a direction number, and a parameter. That right there is the little equation for how the x coordinates work for any point on this line. That's pretty awesome. says, hey, you want to find an x coordinate for any point? Just plug in t, plug in all the values of t that you want, and you find these points in line. Oh, well, at least x coordinates right now. Let's do the y. What's the y start with? Come on, right-siders. What's the y start with? Do you understand how easy it is to get confused between these two numbers right now?
Yeah.
Especially if you're the one who likes to put commas for your vectors. That's why we have these things saying this is a vector, that's a point. You get the point. What's the next thing? Hopefully it's plus. It's going to be plus. We're going to use the sign appropriately. So on this right here, we have literal x, y, and z coordinates. We have literal x, y, and z components of the direction vector. Let's watch the z real careful. Left-siders, you guys, what's the z coordinate of our point? What do we write first? Plus sign, minus sign. What do you think? Minus what? That's it, man. That's the parametric equation for a line. And here's what it says. Give any value of t, same value for all three equations, plug it in, and it'll give you an x coordinate, a y coordinate, and a z coordinate. Put that together, and you have yourself a point. That's how parametric equations work. That's the idea. Now, if I give you this, can you go backwards and tell me a point on that line? It's pretty easy. You'd plug in t equals 0, and that would give you that, we'll call it the initial point or something. It's pretty nice. So you can always find a point on a line by just plugging in t equals 0. It's pretty nice. Can you always tell me a direction vector for that line? Can you tell me the direction, just by looking at it, can you tell me the direction vector? Yeah. 4, 7, -5. Can you tell me the original one? Who cares? I don't care. Because it has the unit vector built in. I don't care that it's the one we got here or not. It's in the same direction. That's a lot of stuff. I'm probably over-talking it, but do you understand the concept here? Do one more thing. Change this into symmetric. See if you can do that. Whenever you're doing this, you got to change back and forth. Change the sign of your x-coordinate, just add it over, subtract it over, and divide by that number. Don't change the sign of this number, please. So this is how this should look. So when I'm going to symmetric, I don't have any more x, y's, and z's generally. There are specific cases, I'll show you that in just a second when you do. But generally, here's how it looks. Like x equals, we don't have that anymore. It's in that equation. So x plus 1 divided by 4. Then we go to the y.
Y plus 7.
Yeah, just like that. That's it. Leave it just like that, and the reason is because it's easy to go back to parametric if you have to. It's easy to see what the point is and what the direction vector is. You start messing with signs, and then it doesn't work so well. You want positive x, positive y, positive z. Everything else, just hold it. Head nod if you're okay with that one. Backtrack just a second. I know we're moving fast, but I want you to get all of it quickly. If I were to give you this direction vector, would you ever use that to build your line? I'm begging you. I don't want to grade that, okay? Please don't make me grade that, because you're probably going to be right, but I don't want to look at fractions. I don't like fractions. What would you multiply by?
12.
Good. How'd you get 12? LCD. Use that. Done. Real nice stuff. Okay, how about this one? What would happen, so we're going to modify the problem. I'm going to do this a lot because I don't have time for 50 examples, even though we're probably going to do like 50. What if that number were 0? How would you write the symmetric equation? Because this would be pretty easy. If this is 0, you just have z equals -1/2. Do you get what I'm talking about? if this is 0, if that's the case, then we really can't write this format anymore because we have that little undefined thing. So here's how it works. If that's 0, we keep these two. And then you put a comma because we can't write it like this, and you wrap it up with the same format over here, this being 0. So it would be the z equals negative 1/2. That's how you would write that. If you ever have a direction number that's 0, parametric doesn't change. You just have a 0 there times t, that's 0. Symmetric, you drop out one of those symmetric equations, leave the 2, you have 1 that's equal to a constant. Now stop and think about this. If you have a variable equal to a constant in 3D, what's it mean? It's on a, this line is on a plane. Look at this happening. X, Y, and Z are changing, right, on this problem. But if it's here, is Z changing? Negative 1/2 on a plane. This is lying on a plane that's parallel to the XY plane, just a half step below. And this is the only crap that's changing, X, Y. Do you guys see what I'm talking about? It's kind of cool, right? That's what's happening here. Let's extend it. I'm going to go back to our original. Do you guys have this written down? Because I'm about to erase it. Are you guys okay with that one? Okay, because I don't want to confuse you with the next one. Can you show line 2, let's say this is line 2, can you show line 2 is parallel to line 1? Can you show, I can show it, I know what I'm doing, man. Can you guys show it? Yes, no?
Yeah.
Okay, here, I'm going to give you 10 seconds. What I want in 10 seconds is, from this line, I want you to find me a point on that line. And I want you to find me the direction vector from that line. Can you do it? Go for it. Can you find me the point, right? So you guys got the point. You guys are going to get the vector. Point. Oh, what's the point start with? 7 or negative 7? Why? Why the opposite sign? Because on the symmetric equation, it's x minus that. So we're changing signs here. So this is 7. What's the y? And the z? I didn't actually hear you. Just kind of imagine you said negative 9. Did you say negative 9?
Yes.
I hope so. I said you guys, huh? Slackers. Come on now. Left-siders, y'all. Can you find the vector, the direction vector?
Yes.
This is the easy part when this is why this format really shines. It's really nice. You know what it is? Denominators. That's all it is. And it's even matched up. X, Y, Z. So this is parentheses or vector bracket. They're important. Now, next question. Come on, stick with me here. Are these two lines parallel?
Yes.
We talked about it earlier. We have a statement up here. Lines are parallel if the direction vectors are scalar multiples. So we're going to write out vector 1, we already have that, man. It's what we used. So if we call that vector 1, vector 2, this vector, is 2 times 4, 7, negative 5. That means it's 2 times vector 1, which means that vector 2 is parallel to vector 1. What's that say to you? What's this all say to you? It says, hey, did you catch that firstly, by the way? You saw, it's pretty easy to see. We divide by the 2. That's why this scalar multiple thing is kind of nice. It's pretty obvious. You go, well, that looks like it's 2 times every number. Huh, what's that say? Well, it says that it's literally 2 times every number. It says it's 2 times that vector. It says these vectors are parallel. What's it say about the lines? This proves that line 1 is parallel to line 2. Or vice versa. Could you go, I'm not going to ask you to, but if I asked you to, could you take this equation and write it as a parametric equation for the line? Could you do that?
Yes.
It would be x equals,
18.
oh boy, we better do it. Okay, we're going to do it. We're going to do it. If you wrote this as a parametric, sorry, my board work's getting a little sloppy here, because I'm kind of thinking of these things off the top of my head, make sure you can actually do them. If you wrote this as a parametric, you're basically solving for x, and these all equal t. So each individual one, you're equaling that to t and solving for x. So we multiply by 8, oh, that's 8t. And then we would add the 7. 7 plus 8t, in that order. You guys okay with that one? If you didn't catch it the first time, here it is again. You're equaling each of these things to t, because that's how we built this equation. So we multiplied 14 times, just imagine the t. 14 times t. It's positive, so we're going to have a plus. It's written in this order. And then we would add the 1/2. Z, imagine equal to a t. We'd multiply by negative 10. We're going to have a minus 10t. We'd subtract the 9. Negative 9 minus 10t. Head nod if you're okay with that one. Are you sometimes going to get different looking lines based on the direction vector that you're using? If I chose to use this vector right here, I'd have a different looking line, even though it's the same line, because the direction vector scalar multiple is still parallel, still through the same point. We can get different looking stuff. If we always simplify our direction vectors, then we get the same stuff. Okay, for real, we covered a lot. Okay, yes, no, maybe. Head nod if you are. What I'd like to do to wrap all this up, I want to show you one more example. I'm going to put one on the board for our break that I want you to think about, and then we're going to come back and pretty much crush it. It'll be a very similar example. I know we're going to go past our break a little bit, but right now I think it's fresh, and I really want to do it. You guys with me? May as well just say yes, because we're going to anyway. So, yeah. I trust you, Professor Leonard. Let's do it. Now I'm putting words in your mouth. I love Calculus 3. Best class ever. I even got a woo. Woo! That was the lamest woo I've ever heard. You go for Space Mountain, you end up on the teacups. That was the woo I just got. Yeah, thanks a lot. All right. I love the teacups, actually. I think they're amazing. For a period of time, we're going to imagine these airplanes are flying in a straight line. Of course, they go around the Earth, right? But for a period of time, we're going to imagine they're flying on a straight line. Okay, so two airplanes. These airplanes are going to go through certain points. They're going to have certain direction vectors. They're going to be flying in a certain direction. So we have plane 1, all the little ones. Plane 2, all the little 2s. With me, yes, no? Here's a question. Do they crash? It's a pretty pertinent question. I don't want to be on a freaking plane, have it crash. You guys are going to buy me a ticket to Disneyland so we can go to the teacups, right? I'm probably going to fly. I'm going to drive all the way down there. So I don't want to crash. Hello? Goodness, you sickos. Don't you want to know? Are they going to crash? What has to happen for two planes to crash? They do have to hit each other. That's eye roll. My wife, awesome eye rolls. Like, seriously, I see him every day. Love you, baby. 3 times a day. Morning, twice at night. Anyhow, no, seriously though, what has to happen for planes to crash? They have to intersect. Of course. What's that mean?
They cannot be parallel.
Okay, that's true. Are non-parallel planes for sure intersecting?
At a point.
If that happened, none of you would ever fly ever. Or if you did, it'd only be once.
Yeah.
Well, it depends.
Because a lot of planes do this.
Depends on the timer.
7th favorite dance move. Mm-hmm. This is why we get to do disco, because our arms don't just all the time. Really hurt, actually. No, not necessarily parallel. Even, what if they did this? Same point. They're crossing a same point. Are they hitting? So in order for us to intersect an actual crash, like an intersection 3 space, with parametric, there's a time associated with it. That's why our times are different. This one took off. It's traveling after a certain period of time from its takeoff. This one's taking off later or sooner. Who cares? But at a certain time. So we need these things to hit a certain point at the exact same time. Does that make sense? That's an aspect of it that we don't have in 2D, really. Unless we're talking about parametric in 2D, and then we do. But with parametric, we have this, in order to get an intersection, you have to have same point at the same time. How in the world do we do that? Well, let's figure it out. This is where our practice comes in. You have lines, done. But let's think about intersections now. Let's think about how do we tell when they cross a coordinate plane? How do we do that stuff? So, number one thing, so in order for them to intersect, they have to cross the same point. They have to cross at the same time. I understand what I'm talking about. Okay. First thing you want to check, let's check if they're parallel, because I do know this. If our planes are parallel, we don't have to bother with the rest of it. Because if our planes are parallel, they are not crossing. Does that make sense? Check parallel right now. What I want you to do, write down the direction vector for plane 1. I want you to write down the direction vector for plane 2. This is not just trivial. Make sure you can write down the direction vector for plane 1 and the direction vector for plane 2, and I want you to check whether the lines are parallel right now. Go for it. I'm going to do it on the board as you're doing it, because you should all be doing it on your own. Lines are super nice because they have the points and they have the direction vectors built in. Just don't mix them up, okay? Don't use points for direction vectors and vice versa. In our case, the ones I got was -2, -3, 1 for plane 1, and 1, 2, -1 for plane 2. Show of hands if you got the same thing I got. Yes, no? That's fantastic. Now, it's pretty easy to see whether they're parallel or not. Are these two vectors, parallel?
No.
They're not parallel. Why not?
They don't have scale.
Since they're not scalar multiple, and it's pretty easy to see, you'd have to multiply it by 1/2. No. No. Not scalar multiples, not parallel. We talked about it though. Does that necessarily mean that these planes are crashing? Same point, same time. Here's how you check that. Here's how you check. If we want to check for an intersection, has to happen is this. Our x1 coordinate, look at the board here. Look, stop whatever you're doing with the board. This is our x coordinate. It's given by when I plug in a time for us, and I get out an x value. Plug in a time, I get out an x value. In order for this to work, this has to equal this. This has to equal this. Our x coordinates have to equal. Our y coordinates have to equal. Our z coordinates have to equal, and they have to all equal at the same exact time. Does that make sense to you? So we set them equal. Okay, well let's let that happen. I want you to set those equal. Do it now. Don't just wait for me to write on the board. I want you to try it. I'm trying to get you to kind of internalize this. When you start just copying stuff down, yeah, that's great, but I know what I'm doing, so you're always going to get it right. I want you to actually do it on your own and go, oh, I did get it right, or I really don't get this yet. That's part of trying to grasp the concept moving beyond just absorbing to participating. I want you to be doing that in this class. What is our x sub 1? What are you writing down right now? What would you write down? Say it in the back louder. That's where it's from, yeah. X sub 1 is 1 minus 2t. But it's 2t sub 1. Make sure you have that little 1. Okay, back people got that one. Front guys. What's that supposed to equal? Come on, quickly.
Negative 3 plus t2.
Perfect. What else has to happen? Well, this would be our x. That's from our x. Let's write the other ones. Write them down on your own as I'm writing down up here. I also need the y's. And the z's. Ooh. I want to ask you if you guys understand where all that stuff's coming from. Right now, what we're doing is we know that they're not parallel, so they might intersect, they might not. I don't know. This is how you check. You check whether the x coordinates are going to be equal, whether the y coordinates are going to be equal, and the z coordinates are going to be equal, and they all better be exactly equal from both equations that we have in order for them to intersect. So, what in the world are we going to do now?
Solve.
How?
Systems.
Systems. How many equations do we have?
3.
How many variables do we got?
3.
2. T1, T2. Parameters have the t's as the variables. There's only 2 variables. With 3 equations, that means we have 1 too many. That's the one you test. Listen carefully. Pick any 2 that you want. I'd pick the easiest ones to make a nice system of. I will make you a promise if you do it right. Pick any 2. I'm going to pick these 2 because I like the fact that I can just add them together and get rid of T2. Do you see what I'm talking about? That's really easy. So I'm going to pick these 2. The 2 that you pick are always going to work. It has to. It's a system. It's the one that you don't pick that determines whether you actually intersect or whether you do not. Did you catch that? That's what's going to happen. So these 2, they're going to be the same. I know what it's going to be. It's going to be the same. But the one I don't pick, this is the one that's going to get you. I'll prove it to you. I just want you to see that. I'm going to talk ahead of it. That way you're like, oh, that's what's happening here. Why? You pick the equations in the system, they will be equal. You're solving for the place where those are equal. The one you don't pick is the one that determines whether you actually intersect or if you get different numbers, then you don't. So pick any 2. Let's pick these. I like this one. I can just add them. Zero. Love getting 0. I know right now the T1 is -1. In 3D world, we think T is time, but it's really not exactly time. It's -1 as, well, it doesn't really matter. -1, maybe an hour before 12 o'clock, who cares? But that's what's happening here. This is going to cross into this point at t equals -1 for airplane number 1. Now, can you find t sub 2? Question?
Shouldn't there be a -1 in the beginning there?
-1 minus
Far
2.
left.
Oh, yeah, okay, sorry.
It is negative.
That looks better. This is why I have you guys here. Catch my errors. I told you it's the little things that get you. For me, it is at least. It's those. I even have an answer right here. I guess I could just look at it, right? -1. From that, can you find T2? Have you all done it? Since I obviously can't do any math today, have you found it? What is it?
2.
Really?
X.
I don't think it's 2. I think it's 6. I'm pretty sure. Did you get 6? Triple check, quadruple check, quintuple check. I don't know any higher than that, so hopefully that's enough. Listen carefully. I don't want to lose you. Honestly, we've done 0 calculus in this class so far. None. We're just working with 3D stuff. Here's what's happening. We solve the system. Airplane 1's going to cross this point at t equals -1. Airplane 2 at t2 equals positive 6. That doesn't tell you anything right now. That doesn't tell you. Here's how you tell. Take these numbers, plug them in respectively for each of these 3. Now here's where the promise comes in. I guarantee you that when you plug in -1 here and positive 6 here, which you should, that's what those numbers mean, it's going to equal the same number. I guarantee you that when you plug in -1 here and you plug in positive 6 here, it's going to equal the same number. Why? That's where I got the system from. It has to. This is the only one that can. So if you're on time on a test and you're like, oh my gosh, I don't know. Don't worry about these two. It's going to work out. Worry about this one. If these two sides, when you plug in -1 and positive 6, if it works out to the same number, these planes crash. If it works out to different numbers, these planes do not crash. Does that make sense to you? Are you sure? I'm getting kind of looks. Yes? Plug it in. Plug this into your system and solve for T2. Yeah. I used this one. So let's try it. So for our X's. If I plug in -1 here, come on, let's stick with me here. If I plug in -1 here, how much is this? Oh boy. How much?
4.
Let's plug in -1 here.
3.
Let's plug in positive 6 here.
3.
Is it the same?
Yes.
Let's plug in -1 here. What is it? Let's plug in positive 6 here. What is it? They're the same. I promised you. Man of my word. Let's plug in -1 here. Be careful with it. How much do you get? You should calculate if you have to. I don't care. How much you get?
2.
Okay. Plug in 6. Are they the same?
No.
Here we plugged in this, we got 3. It equaled 3 when we plugged in here. Here we got it, we got -3. It equaled -3. We got 2, we got 10. That says that these planes do not intersect. They don't intersect. They're missing at that time. That's what's happening. Do you guys get the idea? It's not this. These times are often different. It's, well, they could take off at different times, couldn't they? So they're different times of the day. That's the one that I'm talking about. It's always the one that you didn't pick for your systems. That's the plan. So if you guys feel okay with that idea. Would you like to try another one? Would you like to do that? I'm going to put one on the board. I want you thinking about it. See if you can do it to test yourself. I know we have a break. I'm going to give you a couple extra minutes. You're welcome. See if you can do it. Write it down. I'm going to say just a little blurb, and then I promise that I'm going to break us. Probably breaking you right now. Number one thing, were these lines parallel? Did they intersect?
Yes. Yes.
Did they intersect? No. When you have lines that are not parallel, and they don't intersect, they look like this. These aren't parallel, they're not the same direction, they're not crossing. Those are called skew. Skew lines happen a lot, all right? That's what this tells you. It says at these times, I have x equals 3, I got z equals negative 3, I got y equals 2 and y equals 10. Think about that. You got y equals 2 and y equals 10. They're separated. They're not intersecting. Even if your x and your z coordinates are the same, your y's are not when I have those times. The only place they could possibly intersect would be at these times with the planes respectively. If they're not the same, they're not intersecting. Verify they're not intersecting. Not intersecting. That's called skew. These are skew lines. Here's what I want from us before we take our break. What I want for you to do, number one thing, these two lines I'm going to ask you, are they parallel? Are they skew? Or do they intersect? I want all three answers. Are they parallel? That's talking about the vectors. Find the direction vectors. See if the scalar multiples. That's the easiest question. Okay. Find out if they're parallel. After that, check for the intersection, just like this. If it helps you, and it does, it helps me to write them out like this because it makes checking really easy. This is awkward because they're those symmetric equations. You go, it's hard. Maybe set them up as parametric. That's what I'm going to be doing the first thing. So when I come back, I'm going to crush the problem, but I'm going to do parametric. I'm going to check the direction vectors. I'll check parallel. I'll check intersections, and then we're going to go from there. Do you guys understand what I want you to do? Okay, we'll be back in a second. I told you we're going to crush the problem. We're going to go through it really, really fast. Listen, this is extra. I would have taught you how to do it. But we're going to go through because I know it takes a while to absorb this stuff. So here's the idea. Let's suppose these are planes. Do the planes crash? Number one, the easiest way to check this is, are they parallel? If they are parallel, they don't crash. They do not intersect. Think of planes landing. One lands first, the other lands second. Those things cannot crash. In the air, they're flying the same direction. Now, number one thing, if you ever get symmetric and you don't like it, learn how to change to parametric equations of these lines. So when we do this, just give yourself a little T1 though. That way you know that you're talking about plane number one. multiply an imaginary t1 by negative 2, add the 3. Oh, z1. That's weird. When you get that z1, and there's nothing around there. Well, there is. It's still divided by 1. So in this case, when you have that z1 divided by 1 equals t1, that's what it is. z1 equals t1. There's just no no z coordinate on the point. That's the idea. So this would equal t1. You guys okay with the idea here? L2, same stuff. Multiply the t2 times 3, add the 2. Multiply the imaginary t2 times 2, add the 3.
It's about 1 plus t for z2.
Say that again.
Is that 1 plus t for z2?
For z2. Well, imagine the t2. Okay, what's the denominator? Well, 1. So 1 times the t2, add the 1. So you said 1 plus... Yeah. I need a head nod if you're okay with those things. Now, as soon as you've done that, or from here, it doesn't matter, folks, whatever you feel comfortable with. That's why I'm giving you both, so we get comfortable with them, because you need to be. Next thing, check parallel. What's going to tell you whether these planes are parallel? What's going to tell you? Of... So you need the vectors. Let's find the vectors. Vectors are often easiest from here. You can still find them from here. Vector for plane 1, the direction vector is -1, -2, and 1. Don't forget the 1. It's not 0 because there's a z1 being equal. It's 1 in that case. Same thing right there. You guys okay with the -1, -2, 1? What's the other direction vector? Quickly, please. Yep, here or here, either way, 3, 2, 1. Man, this is about the easiest one I've ever given you to check the parallel. Are these things parallel?
No.
There's no way. They're not scalar multiples, so these are not parallel. Not parallel because they're not scalar multiples, and it's pretty obvious. You don't even have to show that, okay? It's obvious they're not scalar multiples. Next question. If they're not parallel, do they necessarily intersect? They could be skewed. So then we're going to check for the intersection. So the next part, we go, okay, let's see. Can we check for the intersection? If we check for the intersection, it means that the x1 has to equal the x2, y2, y1 and y2 have to be the same, and z1 and z2 have to be the same. So we set these coordinates equal. If you can tell where I got these things from, I'll be very pleased. Can you tell where those things came from? Can you tell where these lines came from? So you can make it from symmetric to parametric? Sweet! Back and forth. Can you make it from either one to the vectors, the direction vectors? Is it readily apparent that these are not parallel?
Yes.
Okay. Is it okay that we got these things equal? Do you see where those come from? So once we have our line, x coordinates have to be equal, and y and z, and it gives you a system. What's the best ones to pick? It doesn't really matter. You can pick anyone, but I would pick those two again, because that T1's real nice. That's why I picked that. If I add these and get my signs correct, so if I add them together, 1, 0, 4, T2, and that 3. You guys all right with that one? What am I going to get when I solve for T2? Negative 1/2. from there, can you find T1? Notice they're not going to be the same in general. That's not what I'm asking. They're not going to be the same in general. If I plug in this here, 1 plus negative 1/2 is positive 1/2. Okay, now if you're out with that one. It's a lot of work. There's a lot of steps here. It starts with, hey, find the vectors. See if they're parallel. If they aren't parallel, you've got to check intersection. Intersection is set all the x, y, and z coordinates equal respectively. You got a system, solve that system, and then take these values, plug them in on both sides, and see what happens. What's the only one that could potentially not be equal? Top, middle, bottom. Because that's where we got our system from, is the top and the bottom. They're going to be the same, I guarantee it. Guaranteed. And I'll show you, though. I'm going to give you the other way besides... I erased it. The other way, so setting them each independently equal, that seems easier for some people. So if I take T1, plug it in here, I get 1/2. If I take T2, plug it in here, I also get, looks like 1/2. Are they the same?
Yes.
They have to be. Let's do it down here. Take T1, put it here. Oh, let's see, that's 1/2. Take T2, put it here. Looks like 1/2. Hey, they're the same. We already talked about that. They are going to be the same. And now if you're okay with that one. You can even do it up here. It doesn't matter. They're the same junk. Now take these two and plug them in to the middle one, or plug them in here. That's where we got it from in the first place. Take T1, plug it in here. Looks like I'm going to get 2. Take T2, plug it in here. Looks like I'm going to get... Oh. Do the planes intersect?
Yes.
They do. Why? Because when I have that time, I get the same exact point. They're not off at any point, at any coordinate. They do intersect. They crash. That's a bad thing. Should you understand the bad thing? So these lines intersect. At what point?
Fine.
Well, you found the point. X1, X2, X1, Y1, Z1, or X2, Y2, Z2, because it's the same thing. They intersect at the point that we just found. That's why we said they intersect, because it was at that point. It seems trivial, but you need to understand that. Are you okay with it? Can you find the angle at which these planes will collide? Well, you need a little note for that. How can we find that? Okay, think about it. How can we find the angle between lines? Lines are given by their direction vectors. How can we find the angle between two lines? Come on, put it together. How can we find the angle between two lines?
You use like the 180 cosine inverse equals line.
Do lines have
Vector
vectors?
one, vector two, or the magnitude.
Do lines have vectors?
Yes.
Can you find the angle between two vectors?
Yes.
Are those vectors kind of like in the lines somewhere? If you find the angle between the direction vectors, you will have found the angle between the lines. Does that make sense? So it's not hard. You've already done it. So in order to find the angle between the planes, which are the lines here, that's a horrible thing. I shouldn't have done that to you, huh? Because we're going to be talking about planes in a little bit. Airplanes.
Are you still gonna go to Disneyland?
That is not relevant right now. Probably not. I can't afford it. It's too expensive. Find the angle between the airplanes, the lines, as they collide. The angle between the lines is the same as the angle between the vectors. So if you can find the angle between vectors, you can find the angle between the lines. No, I have it written down better than this. How many of you right now, given that these lines, well, let's see. Can you tell me the vectors that give us the direction of these lines? Can you tell me the vectors? Specifically, come on, quickly, what's one vector? Can you tell me the other vector? Can you find the angle between those two vectors?
Yes.
Then you will have found the angle between these two lines as they intersect. Let's go, oh, what does that for you? Do you remember the formula? Do you remember how to do that? The vector, or the angle between any lines is given by this. So for us specifically, we go, okay, well, let's do this. Let's take V1 dot with V2 divide by their magnitudes, and then I'm going to put one more thing up here so you don't get confused. Please listen. This right here has the chance to give us either an acute angle or an obtuse angle. If you always want to make this the acute angle, put an absolute value there around that scalar, because dot product gives you a scalar, and that will always give you the acute angle between your lines. Let's do that. Let's keep it an acute angle. That way we don't get two different answers. Does that make sense to you? We're going to keep it acute. It's a cute little angle. Anyway, so do it. Go for it. Find me the angle between those two direction vectors. Find me the angle between the lines, what I'm asking you. Man, do you remember how to do a dot product? Do you remember that at all?
Yeah.
I hope that you do. We've done a lot since then, but hopefully you do. Take the components, multiply them, add them. Here, also take an absolute value so you get the acute angle. Do you remember how to find a magnitude? I know it's got square root. Explain to me in your own words how to find a magnitude of a vector. Come on, quickly. What do you do? Square them. Add them. 1, 4, 1. Nine, 4, 1. Oh, what do you get on that one? So it's -3, -2, that's -5, that's one -4, but absolute value. Hopefully we're getting, oh. Snap, I made a mistake.
-4.
I just saw that, I was like, wait a minute, that doesn't look right. -4. Better check my work again. -3, -1, sorry, +3, -1 is -3. 2, -2, that's -4. 1, 1, that's 1. So if I combine those, I'm getting -6, and absolute value would be +6. Can you give me 6 times 14, if you would? 84. Now, we're in real world land, okay? So I don't care if you rationalize this right now. I want you to give me an approximation for the angle. So for us, we go, okay, theta would be cosine inverse of however you want to write this. You can rationalize and simplify for the exact angle. But this is going to be about how much? I think it gets something in the 40s.
49.1.
49.1. So cosine inverse of this. (49.1 degrees). We just found the angle that these planes are going to crash at. The acute angle because we picked the absolute value. The other one would give us the obtuse angle. Are you understand what I'm talking about? We want the acute angle. Generally, why? Just that's our convention. Now, I don't really want these planes to crash. Oh, wait. Go back. Pop quiz. What if this worked out to be 0? Come on, stick with me. Come on. I know. We have a lot. Okay. What if this worked out to be 0? What if the dot product worked out? The numerator, the dot product worked out to be 0. What would you know about these planes? Meeting right at 90 degrees, perpendicular orthogonal. That's what would be happening. Kind of cool. All right. So that's not, but I want to test you on it. I don't want these planes to intersect. So I'm going to develop a warning system. As soon as plane number 2 enters my little octant here, so my octant is the XY, the YZ, and the XZ planes. As soon as it crosses those things, I'm going to send warnings. And I'm going to say, hey, you're on a collision course. Because I don't want these things to happen if I'm the whatever people that control airplanes do, you know. I don't know. I'm not that guy. I teach math. But what I want to happen, I want to figure out when and where they're going to cross my coordinate planes. Here's how you do that. Now, naturally, I'm making airplanes, but this is just lines intersecting stuff, okay? That's what's going on. So how you figure out where and when we cross the YZ plane, how to do that. Just set the component that gives you that plane equal to 0. So basically, set the component not listed equal to 0. If I'm crossing the XZ plane, that's when, XY plane, that's when Z is 0. If I'm crossing the XZ plane, that's when Y is 0. And if I'm crossing the YZ plane, that's this one, that's when X is 0. Does that make sense? Are you sure? Or are you just nodding your head so I'll shut up and keep on doing this math? No? All right. So whatever plane you want, whatever variable is not listed, set equals 0. Now I'm talking about plane 2, line 2. So line 2 was this one. If I set Z equal to 0, I'm only looking here. This is all I'm looking at. If I'm going to set, there's no Z, there's the Z. If I set Z equal to 0, then T sub 2 equals -1. This is the when. When I'm going to cross the XY plane is when T is -1. Now, can you figure out the point to that? Well, yeah. Now that you got a T sub 2 equals -1, just plug it in. If I plug that in, then I'm going to get the point. So if I plug in -1 here, well, let's see, -3, that looks like a -1 to me. If I plug in -1 here, that looks like +1 to me. If I plug in -1 here, why would I do that? I just set Z equal to 0. It's obviously going to be 0. Verify that that point is actually on the XY plane. Because your Z is 0. That was the whole idea. Does that make sense? Can you do the next two? Can you do that? Try it. Set Y equals 0. Go through it on your own. Don't just wait for me to do it. I'm going to do it in just a minute. If you did it on your own, that's excellent. I at least want the idea understood. If I'm going to cross the xz plane, y has to be 0. Go to the y coordinate, that formula, 0. Y has to be 0. If we solve, this is the when I'm going to cross the xz plane. Take it and plug it in. Of course, y is going to be 0. That's literally how we got it. And then you got a point. That's a point on the xz plane. Same thing happens with the yz plane, and that's the point that we have. I need to show if you understand the concept here. Okay, now planes. Planes are not airplanes, all right? Planes are really cool, and they're really easy. What we're going to do is I'm going to make it through the formula, and the rest of it's just practice. It works very similar to this stuff. There's just one thing that we need to understand about planes before we really get into the nitty-gritty. I'm going to define something that we've talked about, we haven't actually defined yet. It's called a normal. Here's what I've told you about it. What's a normal mean? That idea of perpendicular. Normal specifically means orthogonal or perpendicular to a plane. That's what we say here. Now, because we said, well, normal is 2 vectors. Well, a vector can be contained in a plane, so technically, yes. But when we say a normal vector is a vector perpendicular to a plane. Now, how about this? We're going to build the formula, and then we'll take our break. How about this? How many normal vectors are there to a plane? Here's plane. How many normal vectors come off of that thing? Infinitely many. Are those normal vectors all parallel?
Yes.
Which means they're all scalar multiples. So while there are infinitely many normal vectors, they're all scalar multiples of the same unit normal. Now, we don't need a unit normal, but I'm trying to get you to understand that it doesn't matter. One normal vector is enough to define a plane. Do you understand what I'm talking about? Because all the other ones are just scalar multiples of it. You with me? So, given one point on a plane, and I'm not going to say the, I'm going to say a normal vector to the plane. We can define a specific plane. Here's the idea, like just a rundown of it. Look, you can't define a plane by the vectors that are in it, because there are infinitely many vectors in that plane. Does that make sense? You go, okay, how am I supposed to do that? I don't know. I don't know either. You just can't. There's infinitely many vectors in there. But there's only one normal vector, or scalar multiples of that normal vector. Does that make sense? So a point, something that solidifies where a plane's at, and a normal vector, it's enough to do this stuff. Now, this is why it gets confusing for you people. Look at what you need for a line. You need a point and a vector. Look what you need for a plane. You need a point and a vector. It's the same crap. It's just the type of vector you have, which makes all the difference in the world. If we're talking about lines, you need a point and a vector in the same direction. If you want a plane, you need a point and a vector that is normal. That's the difference. The formulas look very, very similar. You see it, same stuff. It's just the way that we organize that stuff that makes all the difference. You understand? You're going to make some mistakes at it. You're going to use the formula for a plane when I want a line. And you're going to use the formula for a line when I want a plane sometimes. Just when it happens, go, oh crap, I can't do that. Think it through very carefully. What am I actually doing? Do I want to find the equation for a line or for a plane? And do the appropriate thing with that. Does that make sense? So let's build the equation. We'll run through a very quick example. It's not going to be hard. You just need to use the appropriate thing in the appropriate spot. So we're going to take any vector in the plane. It's going to look a lot like the line, so I'm going to move a lot quicker through it, but it's going to look very, very similar. So here you go. Let's start with a vector between 2 points. These points are going to be on the plane. So a vector between 2 points on the plane. Can you give me the vector between 2 points? Of course, we've already done that. So that vector is same thing we started with. You guys are all right with what I'm talking about? So this is two points in the plane. Hey, you find the vector. This vector lies in that plane, lies on the plane. Head nod if you're okay with that one. Now, let's continue. We go, all right. Let's also take a normal. To the plane. Here's the magic. You're actually, I hope that you like this. The proof part's kind of interesting. The formula part, working with it, okay. The proof part's kind of cool. To me. Well, that's super dorky, so, you know, cool is relative, I guess. All right. True or false? True or false? N, a normal vector, has got to be perpendicular to P0 to P. True or false? Is this in the plane?
Yes.
Yeah, that's why we built it that way. Is this perpendicular to the plane?
Yes.
Therefore, it's got to be perpendicular to every vector in that plane. Now, here's the magic. And you know it. Because this is in the plane, n's the normal, it's perpendicular to this because that's in the plane. And now that you're actually with me, I can write that down. How about this one? What do you know about two vectors that are perpendicular? What do you know about that? How do you test for perpendicular vectors? They're which product?
Dot product.
They're dot product. Which way do I want to do it? Yeah, do that. If two vectors are perpendicular, orthogonal, their dot products have to be 0. That's it. That's literally like essentially it. Remember that this happened if and only if these things were perpendicular. That was the only way it happened. So if we have perpendicular, we have to have the dot product equal 0. But I have that vector, and I have that vector. This vector dot with this vector has got to be 0. It's got to be. Here's n. Here's this. I know they're orthogonal. I know the dot product's got to be 0. That's pretty cool. Can we do some work with it? Let's see. X component, Y component, Z component. X component, Y component, Z component. They're just vectors. I can dot product them. So if I do, we get that. Follow along with me. Do you see that we get the scalar function? It has variables in it, so we're going to call it a function, but it's a scalar function. It has number, that's just a number. There, no vector. Number, Y components, multiply them together, add. That's what it is. Take X, take Y, take Z, multiply the components, add them together. It's just we know that that dot product has to be equal. Why? Everyone in class right now, why do we know that dot product has to be equal to 0?
Cosine is.
All I heard was orthogonal. Well, okay, that's good enough for me, man. They're orthogonal. Dot product, 0. Done. Orthogonal. Sweet. Got it. That right there is the standard form equation of a plane. That's literally it. Look at it. If I give you a point, could you plug in the point? If I give you a normal vector, could you plug in the normal vector? Yeah. That's it. Now, what I said standard form there is this. Do you remember like the y minus y1 equals m, x minus x1 thing? Do you remember that? You always start there with a point and a slope. You always start here with a point and a vector, same stuff. And then you like distribute and you add to one side and you get it into the slope-intercept form. Do you remember that? We do the same thing here. So this is called the standard form. It's what we use to get to the next thing. I looks a little bad. This ain't health class, all right? I mean standard form, so don't, whatever. Can I get a little clap? Don't answer that. That's wrong. Sorry, that's a bad joke. I'm ashamed. I'm a little ashamed of that. That was funny. That does not get better. There's a lot better than that. I'm not going to edit it. Enjoy that. Yeah. Tell your friends. I'll tell your friends. If you distribute all this junk, I want you to jump down to here. What happens is we get this AX. We get an actual number. Do you see it? We get, I'll show you. Keep this, and you are going to have three numbers. Direction, the normal vector components times the actual piece, what do you call those things? Coordinates of our point. And they're going to be numbers. If you add or subtract or whatever, get them all to one side, we end up getting this. Now this all looks very fancy. I don't want you to worry about the fancy. I want you to worry about the next thing. Do you see that this is all going to be one number?
Yes.
Just a number. We call that number D. That number D is just all the junk. That's general form. This works so much like point slope into slope intercept. We use a point and a normal to get down to this sort of thing. It's not really slope intercept, but it's a lot easier to work with. This right there doesn't quite give you a point, but it definitely gives you a normal vector really, really easy. Show of hands if you feel okay with what I'm talking about. Are you really getting this? Tell you what. Can we do an example here real fast? Before we do, well, we're going to do a lot more examples when we come back, and we're going to go through everything. Before we do, though, in case anyone just needs to take off, which I hope you don't, but if I had two vectors, imagine 3 points in a plane. Here's my plane. Vector here, vector here. Would you know how to find a normal given two vectors in a plane? What would give you a mutually orthogonal vector to two vectors in a plane? If you have two vectors in a plane, you can always get a normal vector by a, what's everybody? The cross product. This is why you need 3 points to define a plane. Because if I have 3 points, I can go point 1, point 2, point 3. I'm going to draw on my paper. I got a whiteboard. 3 points. Vector 1, vector 2. If I do a cross product, that's my normal. That's why you need 3 points, because 3 points defines 2 vectors. And 2 vectors you can cross product, and you can cross product, you get a normal. And if you have a point and now a normal, we have a plane. That's the idea. That's pretty darn cool. Let's do our one example, then we're going to take our break. Pretty basic example. You know, a lot of times, people get equations of lines and equations of planes really jacked up. So I need you to be really good at that. I want to find the equation of a plane, so we're going to be using this stuff, equations of planes, but I want it through a point, and I want it parallel to this thing that I've given you. Now, what 2 things you need to find the equation of a plane? What 2 things? A point and what type of vector? Normal vector for a plane. What have I given you here? Is this a line or is this a plane? What is that?
Plane.
Lines have this, the x equals, y equals, z equals. Do you see that? They have equal signs everywhere, like everywhere. They're either fractions equal or x, y, and z equal. Do I have that? What is this thing then? This is a plane, for sure. Can you right now tell me the normal vector to that plane? Can you tell me right now? Don't say it out loud, just write it down if you can. Write down what the normal vector to that plane is. Go. It's a plane. It's a plane. If these planes are parallel, I can't do it as a paper. If these planes are parallel, tell me something about their normal vectors. Tell me something about 2 lines that are parallel. Tell me something about 2 lines that are parallel.
Same slope.
Same slope. Or in 3D, same vector. Same direction, scalar multiples. So if these 2 planes are parallel to each other, tell me something about their normal vectors. Can they be anything else but the same vector? No. So whenever I ask you, hey, find the equation of a plane that's parallel to another plane, if you can find the normal vector to a parallel plane, you have found the normal vector that we are looking for. Does that make sense to you? It's not super hard, but you got to think like this. So if planes are parallel, they have the same normal vector. And I know you wrote it down. Our normal vector here is, what is it?
2, 3.
Okay, let's try it again. Come on, 20-second recap. There's 2 things you need to write the equation of a plane. What's one of those things? Come on, losing you. Goodness. There's two things you need to write the equation of a plane. You gotta have a point. Do we have a point? Do we have a normal vector?
Yes.
How did we find that normal vector? ABCs, man. ABC. Easy as 1, 2, 3. Oh, you like what I did there? Now I see. ABC. Let's do calculus, you and me now. No, that's how it goes. I'm pretty sure Michael Jackson told me. You can't anymore. You're asleep? Oh, too soon. Love you, Michael. I'm gonna get some negative comments on that one. So, listen, if planes are parallel, they have the same normal, or at least scalar multiples of the same normal. So use the same freaking one. That's fine. So use the same exact normal. So parallel, same normal. Parallel lines, same vector. Parallel planes, same vector. You see the connection. We need a point and a normal. We have a point and a normal. And here's how to work with the rest of it. Literally take these numbers, put them in this spot. Don't try to put it here. Put it here. We use this to get to here. It's easy to get the numbers screwed up. It really is. It's really easy to put these numbers here if you're not paying attention. So here's how I always think about it. X's and x coordinates go together. That's what that stands for. So if I build it, I know I have to have an x minus 3 because that's the x point. That's x coordinate of that point. And then the vector is what goes on the outside. X minus 3, I get y minus 6. I get the 3 because that's my normal vector component for y. Am I going to have a plus or a minus? Should I do plus or minus? Watch your signs. And then z plus 1, or sorry, z plus 2, z minus 2. What's that one?
Plus 2.
What's it equal? Because it's got to equal something. Mm-hmm. Nature of the dot product of perpendicular vectors giving us 0. That's where it's built off of. Do you leave it like that?
No.
Heavens no. Don't leave it like that. Distribute, get it into this form. So we're going to do it fast and then stop for a while. This is what we did right here with all this junk hanging out. And then we took all the junk, this stuff, the sub-zeros, and we added it or subtracted it over. That's what's going on here. So right here we have our 2x, we got our 3y, we got our minus z, we got our negative 6, our negative 18, and our negative 2. Take those numbers and move them. That's what I want to see. I'm going to do it all at once. I think that we get, let's see, negative 26 over here. So when I add it, it becomes positive 26. Should I feel okay with that one? Hey, here's a way to check your work. Look here. Look at the vector you use for your normal. If you don't have the same exact numbers, you've done something wrong. That's how to check your work really fast. If you have these numbers in these spots, you've done something majorly wrong. Did it make sense to you? From here on out, it's going to be a lot of practice, but we're going to take a break for a little bit. Okay, hey, our time for a lot of practice. As we were just talking about, the two biggest things you need is a point and a normal vector. So in the next examples, that's really all we're going to be talking about. Is how to find the point, how to find the normal vector. Because if you can find that, you have the equation of a plane. It's like point slope. It's not bad. So let's take a look at this one. Find the equation of a plane containing 3 points. Kind of gave it away last time, but when we talk about a plane containing 3 points, the idea is you need what do you need for a plane? Come on, what do you need? Point and normal vector. Do you have a point? Now you got 3 of them. Do you get a normal vector? No. Can you find one?
Yes.
Yeah. So if I give you 3 points, the idea is let's figure out what the vectors are that connect those 3 points, and then if I have 2 vectors, a cross product always gives us a normal. There's one advice though. You gotta use the same point twice. So if you're gonna go P to Q, you gotta go P to R because you need that that cross product to actually work from that, let's call it a pivot point, okay? From that point P or Q or R, doesn't matter, but I'm going to do it this way. So I'm going to find PQ, that vector from P to Q. You guys help me out with it. Come on, let's work quickly, but let's work. What is it?
-1.
That's the vector from P to Q, for sure. Head nod if you're okay with that one. The vector from... Which should I go from?
P to R.
Q to R?
P to R.
P to R. Okay, same one. What's that?
-3.
-1.
Beautiful. Show of hands feel okay with that one. Now, what are those vectors? Where are they? Oh, they're in the plane. Yeah, they're on the plane, in the plane, same thing. They're on the plane. Are they a normal vector?
No.
No, but if I take them and I, what's that thing again? Cross product them. A cross product gives us a vector that's orthogonal to both of them. If it's orthogonal to both of them, they're both in the plane, it's orthogonal to the plane. So it's a normal vector. So let's go ahead, let's find it. Our normal vector is going to be the cross product of whatever vector connects your, whatever two vectors connect your 3 points. In this case, I can't even write anymore, PQ and PR. Now, here's a good question. Do you know how to do a cross product? I think I pretty much murdered you with homework enough that you can do this like in your sleep. I hope I did. Bless you. Calculators do it too, I think. So you can do that. What do you start with?
I, J, F.
I'm going to ask you kind of an interesting question. Does the order matter? Does the order matter? I mean, ultimately, I know I'm going to get a different answer, but does the order matter? Would a normal vector going this way be any different than a normal vector going this way? Only by the sign. And since we can factor out scalar multiples, it doesn't really matter. It doesn't matter. It doesn't matter at all. As long as you have two vectors in the plane and you are starting from the same point, cross product them, you're going to find a normal vector. That's all we're looking for. In fact, it probably doesn't even matter that you start with the same point, because if you cross product any two vectors in the plane, you're going to get a normal vector. I just like to do it so the cross product makes a little more sense. Does that make sense to you? Hopefully it makes sense. I'm hoping that you've been doing as I've been rambling. Have you been doing as I've been? You haven't. Darn you people. Do as I ramble. So the idea again, as you're working, because I know it's going to take a little time, as you're working, I don't care about vectors in the plane for the nature that they're in the plane. That doesn't help me. So that's in the plane, yeah. That's in the plane, yeah. That's not how we define planes. So whenever we find two vectors in the plane, that's great. Cross product them. So when we need a normal, not just a vector. So if I cross product these two vectors, that's what's giving me my normal. Then I'll have a point, any one you want. And I'll have a normal, the thing that we just worked so hard to find, and that's how we define our plane. So let's see. What'd you get? I'm just going to give you answers from now on. I can't afford to go through all the work like over and over and over again. So do y'all feel comfortable on finding the cross product?
Yes.
Okay, what I got out of this was negative 21i minus 7j minus 14k. Did you get the same thing?
Yes.
I mentioned something earlier. You notice it's going to be a lot of recap, but I mentioned something earlier. You can manipulate your vectors as long as they don't deal with a distance. This doesn't deal with a distance. It's just a direction. That's nasty, folks. That's nasty. Can you make it look better? More better? Make it look more better. How are you going to make it look more better? I'd factor the negative for sure. And the 7. So if I do that, what's it doing? Well, it's taking this vector and it's moving it here and it's shortening it. Who cares? It's still a normal vector. It's still orthogonal to that plane. Is that logic making sense to you? If you reverse these and did the cross product backwards, it'd be plus, plus, plus. You'd still have to factor out the 7. But you see, it doesn't matter. Orders, you can always change the scalar multiple of that. So, again, 2 things we need for a plane order, 2 things quickly. What are they? Point and...
Normal vector.
Do we have a point?
Yes.
Write down any one you want. I'm going to write down the P. Have we managed to find a normal vector?
Yes.
Which one are you going to use?
The one.
Not this one.
No.
Simplify. You're going to get
3i.
Plus J plus 2K.
beautiful. Could you change that to the vector brackets and be just fine? I don't care how you do it. We're going to use both in this class. So from here, we've got a point, we've got a vector. What I want you to do, if you haven't done it already, I want you to fill out the formula for a line or a plane. Stop for just a second. I know you're working. Look up here for a minute. Do you see that both formulas have exactly the same junk in them? A point and a vector? So if you're not really minding your P's and Q's, you can put it in the wrong formula really easily. You can go, oh yeah, I'm finding a line. You're not finding a line. You're not finding a line. If you did, you'd be finding a line that is perpendicular to a plane through that point. That's interesting, but it's not what I'm looking for. I want you to define the plane in this case. So use the appropriate formula, even though you have the same looking stuff. It looks a lot alike. Be careful, okay? So for us, go ahead and figure that one out. And I'm going to give you the answer in just a little bit. I want you to double. Go ahead.
For this -7, is that negative or is it positive?
If I divide by -7,
Oh no, on the top, is that supposed to be negative or is it positive?
for this, I don't know. Let's find out. -5 plus 12 is 7, but remember there's a minus. That happens a lot. Remember I did the minus like 14 underlines? Yeah, happens all the time. So we have this, we have our normal vector components here, here, and here. We got our coordinates for a point here, here, and here. Make sure your signs are okay. Distribute. Did you guys do this and get a final answer for me? I got 3x plus y plus 2z equals...
7.
Beautiful. Ten points on the test, right there. Just very basic, very basic. But I'd give you something like this because it uses the cross product. It uses your understanding of how to do stuff like that. Does that make sense to you? That's how I test you on these things, is with composite problems. We don't have enough time for me to test you on every little thing. So I make big problems that way you have to work through them to understand the concept. Do you? How do you check your work?
See if it comes up with the
Yeah.
hope that you're right.
Same thing, that's how you check your work. Let's do the next one. I want to find the equation of a plane that has that point in it and contains this line. Now, we need a few things, right? We need a few things for a plane. We need a point, and we need a normal vector. True or false? This has a normal vector in it.
No.
No. If the plane contains a line, so if this is my plane, I draw my line, tell me what that line is giving me. What do lines have? They have a vector in them. What else do they have? They got a point in there. We got a point on that. So this line gives me really two things. It gives me a vector in the plane. It also gives me another point in that plane. Does that make sense to you? This is a weird problem. So I want to identify everything we got going on. What junk do we know about in the plane? Well, I know that there's a point in that plane. I know there's a point in that plane. The line also gives me, so if the plane contains a line, that line also gives me a point in that plane. Not sure if you follow that logic. The line's in the plane, and the point's on the line. The point's on the plane. Tell me a point on that line. We'll call it Q.
2, -1.
2, I like the 2. Do you see where the 2's coming from?
-1.
Where's it? -1.
Yes.
-3.
That's a point on the line. Therefore, it's also in the plane because that line's got to be in the plane. Show of hands feel okay with that's a weird concept. I want to make sure you guys get it. You guys okay with that one? Now, how about this? What else does the line have? Vector. So if that line is in the plane, that vector can be thought of as contained in the plane. Let's write the vector. I'm going to call it B. So this is from our line. Our line's got a point. Hey, 2, -1, -3. Our line's got a vector. Oh man, you should be really good at finding direction vectors at this point. Come on, like 5 seconds. What's the direction vector for that line?
2, -3, 5.
Use the correct notation. It's got to have a bracket.
For P, was that given?
Yup. My daddy always said, yup, give him. He wasn't Texan. I think he's from California. We talk like that. It's because it's cool. Not really. He's a math teacher too. Yeah. It's a line of dorks, like all the way. like grandfather was a teacher. Yeah, seriously, I don't know, a lot. Anyway, the logic is this. Look, you're gonna have to find what type of a vector to describe a plane.
Normal.
If it's not given to you, you're going to be doing a cross product probably, or finding something else from another plane. But right now we go, okay, I don't have anything that's telling me a normal vector, so I'm going to have a cross product. Well, in order to find a cross product, how many vectors do you need for a cross product? Do I have one?
Yes.
That's in the plane. You guys get what I'm talking about? That's in the plane. This is one vector. Can you find another vector in the plane?
Yes.
How? Yes, because those are both in the plane. See, it's not hard, but you see how you have to think about these things a little strange? Let me walk you through it if you didn't catch it the first time, okay? Check it out. Point P, got to be in the plane. Make sense? This line is in the plane, which means that point is in the plane, and that vector can be thought of as being in that plane. Does that make sense? So if I have one vector here, and I say, well, let's define vector A as P to Q, then I get another vector. -1, 3, -8?
Yes.
Cool. Show of hands feel okay with the thought process so far. So we had a couple points, find a vector. We were given a vector in the plane, no problem. Now I have 2 vectors that are in the plane. Are you still with me? What is your next step?
Crossfire.
Find it.
I actually have a question about choosing which one should be in front to subtract, because isn't the vector B connected to point Q?
No. It goes through there. But connected, it's weird, right? Because these vectors are position vectors. They're not connected at all. It's a scalar multiple to get up to there. So we think of it more like, here's the point, and here's the direction you're headed through that point. So it doesn't really matter. It doesn't really matter which one you subtract from which. And we found that out over here too, right? Because even if you cross product these a little funky, you're still going to find a normal vector. Okay, so point in the plane, yep, check. Line in the plane, okay, that has a point, that has a vector. So I've got a vector, I've got another vector, that's 2 vectors. Let's let our normal be the cross product of the vectors. Oh, nastiness. I want to make sure you get the same thing I'm getting. Did you get, if you did it this way, did you get negative 9i minus 11j minus 3k? Did you get that vector?
Yes.
Yes.
What's the first thing you're doing with this nasty vector?
Factoring in negative.
Probably removing what?
Negative.
Yeah, factoring out the negative, because I don't want to deal with all negatives. That's really ugly. So I would multiply or divide by -1, whatever you want to do. Listen, I told you we're going to move a little quick on these topics because I want to get through a lot of stuff here, but I want to make sure I'm also clear. Are you guys okay on getting all the way down to at least the idea of you have two vectors and finding the idea of the cross product? Yes, no?
Yes.
From here, if you can find your normal vector and you have a point already, can you just define the plane? I'm going to leave it to you. Here's the final answers that we would do. So our plane would be just using the equation of a plane. We got my normal vector. Here's 9, 11, 3. I got my point. Here's -3 plus 4 minus 5. And if we go ahead and distribute and take all of the constants and move them off to the right-hand side, which we're supposed to do, I got -2. Did you get -2 as well?
Yeah.
What did we just find? Is that a line or is that a plane?
Plane.
It's a plane. It's a plane that contains this point and that line. That's the idea. Okay, we got a few more things to do. Next one's a little weird. They're all weird. Okay, they're all a little weird. I'm trying to give you the weird ones so that way I kind of teach you how to think about them. Are you having fun? At least a little bit.
Yes.
Yeah.
Am I beating your brains into submission though?
No,
No? Good. All right, I love that. Sometimes I look out there and ask that question, you go, it's little tears, like little tears. It's like math. I see like pluses and minuses. Okay. In order so that I can get more weird ideas in your head, like math weird, okay, not real weird, but like more weird ideas in your head, what I'm going to do is I'm going to give you the example. We're going to talk mostly about the idea of how you do it, and then I'm going to give you the answer, but you're expected to be able to go from there. A lot of it is just thinking about it. So I want to plane with these 2 points. I'm going to draw this one for you so you see it. What I want here, I want a plane with 2 points in it. From which I can get a vector. Notice from any 2 points I can get a vector, so I can automatically get a vector in that plane. That's not the problem. Does that make sense to you? Are you sure? The problem is this one. I also want it perpendicular to this other plane. So I get this plane flying out here that's perpendicular to this plane. So basically I have this. Can you see the picture I'm trying to draw for you? I want you to think of a plane here and then a plane that's smashed up against it. Now here's the point of this. Listen carefully. If you close your ears for a second, you're going to miss it. If you blink, you're going to miss it. You guys okay on finding that vector, yeah? This one's pretty easy because I got 2 points, P and Q. You can find a vector. How many vectors do you need in order to find a normal? I have 1. I'll be able to find 1. I need another one, but check this out. If this, listen carefully, if this plane is perpendicular to this plane, what's the normal of the purple plane gotta do?
Parallels.
Which means you can fit it in that plane. Does that make sense? So if the purple plane is perpendicular, purple perpendicular, I say that 3 times fast, to the black plane, the purple plane's got a normal. If it's perpendicular, then the normal to my purple plane has got to be in the black plane. The normal has to be contained in that. Well, it has to be at least parallel to that plane. It's got to be able to be put in that plane. So this whole thing, the perpendicular to the plane, it means that the normal to this plane must be into the one we're trying to find. It's got to be. So I'm going to do it on your own. Well, I'm going to have you do it on your own. But here's the idea. Well, I've already given it to you, but the rundown. The rundown is, number one thing, if we find a vector from P to Q, you need to be able to find that. That's the vector from P to Q. You can probably see it right now. If we have the normal from that plane, can you find the normal from that plane? I like it. It's pretty easy. If I find the normal from that plane, then, man, the normal for the plane we want to find it's got to be that normal. We'll run through it like one more time, then I'm gonna give you an answer. Got a couple points. You can find a vector. That's the vector. I've got a plane that's perpendicular. If a plane's perpendicular to another plane, the normal from your perpendicular plane, it's got to lie in the plane you're trying to find. That gives me 1, 2 vectors. 2 vectors. With any 2 vectors, you can find a cross product. If this vector's in the plane and this vector's in the plane, cross product says I get a normal for that plane. That's what this says. Then my normal can be, hey, take V, cross it with N1. You know how to do a dot product. I'm going to give you the answer. This is 11, 10, 13. Of course, I want you to try this on your own. Walk through it. Make sure you can get this vector. You understand where this is coming from. You get the idea that these 2 things are in here, in this plane you're trying to find. Therefore, my cross product is actually going to work for us. This is my normal vector. Now, do I have a point?
Yes.
Which point do you want to use?
P.
Doesn't matter. Do you have a normal vector?
Yes.
Now that you did the cross product, yeah, you do. So when I put that all together, I've got point. I've got normal. And all this yields when I put it together that right there. That's the plane that we would just find. We would find. I'm going to make a couple statements. We're going to talk about 2 more examples, and then we're going to call it good. I want you to think of this. We've already spoken of it, but I'm just going to write it down for you. How do you know when planes are parallel?
Since,
When they're
Scalar multiples.
planes. What do planes have? You can't just say planes, scalar multiples. Well, you're right, part of it. What has to be scalar multiples? They're vectors. What type of vectors do planes have? So, planes are parallel if their normals are parallel. Does that make sense to you? Planes are perpendicular if their normals are perpendicular. That's a cool thought. Planes are perpendicular if their normals are perpendicular. Also, this is a cool one too. Works with the angle properties from geometry, but to find the angle between your planes, find the angle between the normals. And you can find the angle between the planes. It's pretty cool too. So those three statements are our next notes. We're going to do just a couple examples and be good. So number one, two planes are parallel if their norms or normals are parallel. Two planes are perpendicular if their normals are perpendicular. And the angle between the planes is the angle between the normals. So let's see if we can describe the relationship here. Here's going to be my test question to you. Did you catch that little hint? Subtle. The test question is, describe the relationship. Are these planes parallel, perpendicular, or neither? If they're neither, find the angle between them. It's pretty straightforward enough, right? If you understand the concept. What's your first order of business in doing this problem? What would you do? See if water parallel. By doing what? What do you need to check? If you do,
Second if they're normal. Find the normal.
you got to find the vectors. You got to at least find the vectors. It's how we're defining these planes. Okay, so find the vectors. Do that right now. Find the normal vectors, and then I want you to go through it on your own. I'm going to go very fast in about a minute. Okay, I want you to find the normal vectors first. Determine if they're parallel. Scalar multiples. Determine if they're orthogonal. Dot product. And if they're neither, find the angle between them. If they're perpendicular, obviously the angle is 90 degrees. If they're parallel, angle is 0. And I got 3, -1, 2. Did you get the same thing I got?
Yes.
I got 2, 3, 1. Did you get the same thing I got? Are those normals parallel?
No.
Are the planes parallel? No, because the normals are not parallel. So they're not parallel because why? How would you state that? Are the planes perpendicular? This is what it would take to figure out if the, do you remember the dot product? If the dot product is what number, then we have perpendicular. Perfect, that's how you check. So we'll do sorry about that. If we do the dot product and it's not 0, then we have not perpendicular. So we'll try it. Not 0. Did you get not 0? Did you get 5?
Yes.
It's important. Here's why it's important. So, not 0, not perpendicular. But on the test, on your homework, in real life, you go, okay, well, look, if they're not parallel and they're not perpendicular, what's the angle between them? Can you figure it out? Recall that the cosine of the angle is that, the dot product divided by the magnitudes. Does it make sense on what I'm talking about? You've seen it before. You've seen it a long time ago. Would you please just be smart about it? Watch. Please watch. Watch the rundown. This can be done really, really quick. I don't want you to waste your time on your test because you don't really understand it, okay? Normals, no problem. Scalar multiples, nope, they're not parallel. Dot product, not 0, not perpendicular. That means that these things meet, and they meet at an angle. What's the angle? Well, it's the dot product divided by the magnitudes. Please use that. You've already figured out the dot product. That's why we actually write it down. So this is 5. Do you understand where the 5 is coming from? That's the dot product. And then all we got to do is divide by the magnitudes. That's pretty easy. This is 9, 10, 11, 12, 13. Square root of 14. Square root of 14. Not bad. Angle's cosine inverse of 5/14. Looks like it's about 69.1 degrees. That is my favorite temperature, by the way. I love that temperature. It's so comfortable. It is, seriously. Like, right under 70 degrees. Beautiful. Beautiful weather. How do you find the angle between a line and a plane? I want you to think about this. We're not going to actually do an example, but I need to show it to you. Lines always get direction vectors, no matter what. Planes get normal vectors, no matter what. That's what planes have, that's what lines have. So here's the deal. Here's the deal, though. If this is my plane and that's my line, that's my vector, but the normal doesn't go this way. The normal goes this way. The normal goes that way. Does that make sense to you? Watch carefully so you don't miss it. If I do this, will it give me the angle here? Please watch carefully. When you dot product divide by the magnitudes, that gives you the cosine of the angle that is between these two vectors. This is not between these two vectors. That is between those two vectors. And in order to figure out the acute one, I do the absolute value to keep it positive, to keep that thing acute. Head nod if you're okay with that one. Well, wait a minute. That's not the question. The question is, how do I figure out that angle? Use your geometry. Use your geometry a little bit. How much is all of my
180.
90 is already taken up? So if I do 90 minus whatever that angle is, then I will have that angle. So in our case, if you ever want to find the angle between a line and a plane, the angle is, hey, take your 90 degrees, subtract cosine inverse of this thing. This is to keep it positive. Keep it positive and make an acute angle. You have to have that because you're subtracting from 90. The idea is, if you do this, you're going to find the angle between the normal and the line, the direction vector. If I take 90 minus cosine inverse of that scenario, I find that angle. 90 minus that gives us the angle between the plane and the line. Head nod if you're okay with that one. Okay, last thing, because I know I'm getting tired, and I can tell that you're getting tired. If you ever need to find the intersection of where a line intersects a plane, intersection of line and plane. Plug the line into the plane. Actually, this is even easier. Here, do this. You got a plane. You got etc. Okay, you have X, Y, and Z. If you take this stuff, here's your X, it's same X. Take this, plug it in for X. Take the next one, plug it in for Y. Take the next one, plug it in for Z. You can easily find the intersection. Do you guys want to do one, or are you okay with it? Okay, let's do it next time, all right? Let's do it next time. All right, so back at it for lines and planes. There was something we stopped on last time. How to find the intersection of a plane and a line. I told you it's very easy. We're going to do it with an example. Here's how you find an intersection of a plane and a line. Literally, take the line, plug it into the plane. If we have an expression for X, an expression for Y, an expression for Z, and our plane has that, substituting these in will let us solve for T. Taking that T and putting it in for the line will give us a point on the line. That will let us solve for the intersection of the plane and the line. So what that would look like, take our plane, X is 2 plus 3t. Y, negative 1 plus t. Minus z, just don't forget parentheses. 3 minus 2t, and that still equals 9. So we're just taking our x coordinates, really, equations for those, parametric, plugging them into our plane, and solving. When we do that, I'm sure that you can You can do this on your own. What we end up getting here, let's see, make sure I'm right. If you solve this, you're going to ultimately, and maybe you can check my work and let me know in a couple minutes if I'm right, you get t equals 1. Now, t equals 1 is not a point. T equals 1 is more like a time. Well, if we have an equation that translates time into points, x, y, and z, we can take that, put it here, and then you can tell me a point on the line at the place where it crosses the plane. Does that make sense to you? So it's pretty straightforward. Take the line, plug it into the plane, solve it for t, and then put that back in. So when we do that, we get this point, looks like 5, 0, 1. That would be the point where that line crosses that particular plane. Are you guys okay on the idea behind it? We're covering more kind of ideas right now. This one we're going to thoroughly do, but it's kind of an idea concept. I want to find the equation for a line of intersection between two planes. Like, what? Well, wait a second. If planes aren't parallel, will they cross?
No.
If planes are not parallel, will they cross?
Yes.
They're not like lines. Lines can be skewed. Planes cannot be. Planes go forever, right? These sheets. If they're somewhere in space and they are not parallel, they will cross somewhere. That is going to happen. I want to find, and when they cross, they're going to make a line. The crossing of those two planes, just like the XY plane and the YZ plane cross, right? They make a line, and that line is an axis that we have. So we're going to get kind of an axis, but not along a regular axis. One that goes along whatever two planes I tell you. These two planes. Head nod if you're okay with that one. Well, let's first figure out the relationship of those two planes. Can you find, right now, and you should be able to, can you find, oh, it's a good review, the normals for those two planes? I'm going to give you 15 seconds. Write down the two normals. Let's have N1 and N2. I love planes. I love them because the normals are so nice. So nice to find. What's the normal for this one? Let's get a little bit more enthusiasm behind that one. Goodness gracious. How about this one? What's that one?
1, 4, 2.
You don't get to yell at me. Jeez, goodness gracious. Just joking. Yeah, those are the normals. Okay, let's describe the relationship between the planes. I told you that these planes are going to intersect unless they're parallel. Are the planes parallel? Why not? Because the normals aren't parallel, and the relationship between the normals is the relationship between the planes. If they're parallel, the planes are parallel. If they're not, if they're perpendicular, the planes are perpendicular. These are not parallel. You can tell they're not scalar multiples. They're also not perpendicular. They're not perpendicular because if you did the what product, the dot product is not 0. Here, you can do it right now. 2 minus 12 minus 8, not 0. Does that make sense? So they're not parallel. They are not perpendicular. They will for sure cross because they're not parallel. What I want to do, I want to find the equation of a line of intersection of these two planes. Now, what do lines of intersection even, what do they need? There's two things lines always need to come on. What do they need? Point. We'll talk about the point last because you're probably going to think it's more difficult. The vector is actually very, very easy. You just need to see it one time, and then you'll get it. Check it out. I'm going to draw you a picture over here. Here's a plane. Here's the other plane. Can you see the line of intersection I'm trying to draw right there? This is the line of intersection. Now, we define planes by their Starts with an N, rhymes with ormal. Geniuses, all of you. That's exactly right. You're so good at this stuff. You are good at this stuff. But they're defined by the normals, the normal vectors. What do normal vectors do with planes? What's the relationship there? Right like that. Which means this normal is coming out the perpendicular. Correct?
Yeah.
And if these are not parallel, this also has a normal. Coming out there perpendicular. Those vectors are going to meet somewhere. Or the scalar multiples of the vectors are going to meet somewhere. It doesn't really matter if they're scalar multiples. They are going in the same direction. Therefore, they are going to meet somewhere. Two normals of these planes are going to meet. Does that make sense? Now here's the beautiful idea. That line, that direction of intersection, has to be orthogonal to both of those normals. Do you see it? Has to be orthogonal to both those normals. So the direction that's going, those planes are meeting, right? They've got normals that are meeting. If those planes are like this and the normals like this, the line is going parallel to whatever is mutually orthogonal to the direction of the normal vectors. How do you find the direction that is mutually orthogonal to two vectors? How do you do it? So if you ever want to find the line of intersection or the direction of the line of intersection of two planes, we just have to take our normal vectors, check it out again, normal 1, normal 2, they're going to meet. The directional line has to be orthogonal to both of those. Otherwise, it would meet, and the normals wouldn't make sense anymore. It has to go straight away from it. So I need a vector that's in the direction that's mutually orthogonal to both of those vectors. That is a cross product. We go, oh, that's sweet. So if I want to find the direction vector of the line of intersection, I take the normals from my two planes and I cross them. Let me ask you something. If I ask you right now to find, that hurt when I slammed that down. My normal vector made a hurt on my plane. You see that? It's like bang. It hurt. Hands are all scarred up anyway. If I asked you right now to find the cross product, could you do it?
Yes.
Has anyone done it?
Yes.
Make sure I got that right. I got negative 10i plus 11j plus 8j plus 11k. Looks like that's what I got here too. Did you guys get the same thing that I got? What is it that we just found?
Direction vector.
Cross product, but it stands for, in this case, the direction vector of our line. Okay, we need two things for a plane. We need a point and a vector, a direction vector. We have that now. This is my v. So that's not bad. Now the point. The point is really interesting. What we do for the point. What we do for the point. Set x or y or z, anyone that you choose, equal to 0 in this system. And here's the whole point of this. Here's why it works, because it's not intuitive at first. If you set something equal to 0 and you have a system, if you've got a system, that system stands for the intersection. These planes intersect in a line. So if I set something equal to 0 in this system, which stands for a line, then what we're going to figure out is where that line crosses the particular axis, particular plane in space. So if I set y equal to 0, y equal to 0 is on the xz plane. Did you guys get it? If I set y equal to 0, I figure out where this system, the line, intersects that plane. And that would intersect at a point. And I'm looking for the point. Do you guys get the point? Let me repeat it. Do you understand that where planes meet is a line?
Yeah.
So the system is a line. If I set one variable equal to 0, I'm figuring out where the line crosses a plane. That's what plane? It doesn't really matter. So pick y equals 0. Why? Well, why do I pick y? Because that's nice to deal with, and this is not as nice. So I'm picking y equals 0 to get rid of that guy. So set y equals 0 or x equals 0 or z, whichever one you want. It would come out different because you'd have a different point for each of the 3 planes. So you'll get something a little different. Doesn't really matter. You can get different answers here. Set x or y or z equal to 0. Me, I'm going to pick y. In the system. Maybe this will make a little more sense the second time through that I go through it here. Do you know where the y's went? Gone! Zeros! What are the only 2 variables left?
X.
That means it's going to be on the xz plane. Where y is 0, you're on the xz plane. We're going to find the point. The point is going to give us a point, xz. We're going to find the point where this system, the line of intersection, the 2 planes, hits the xz plane. That's what these variables mean. You gotta know what the variables mean. I don't want to just, hey, this is what you do. I want you to understand it. You guys hopefully now get that when 2 planes meet, they make a line. If I set the system, which is a line, the intersection of the system, that's a line. If I set one of those variables equal to 0, I'm figuring out where it crosses the plane of the variables I'm left with. In this case, you go, okay, well, I'd probably multiply this by 2. I think I'd add them. I'm not going to show you the rest of the work, but to find the rest of the work, we just take that value, plug it into either one of these equations here, and you can solve for your z. Are you guys okay with what I'm talking about? Your x, I'm going to rewrite it. Now let me think about it. What would the y be?
0.
Well, I set it equal to. And z, if you substitute in, which I want you to try on your own at some point, is negative 11 over 8. What is that? It's a point. What particular point? Listen, we just need, please listen, this wasn't supposed to be magic. We just needed any point on that line. Does that make sense? Any point would do. How do you find it? Well, we just wanted to find the point where it crosses a plane, because that's the easiest thing to do right now. How are you supposed to find a point if you don't know where it crosses anything? All we knew was a vector in the direction. We didn't have a point. So we have to use this sort of system idea to find at least some point. Now, do we have a point and a vector?
Yes.
What are we trying to find again? An equation of a plane or an equation of a line? Let's use the appropriate thing, okay? This is very easy. I talked about last time to get confused between these things. You go, oh, now it's plugging into a plane. We're not finding a plane, folks. We have a direction vector. Direction. We've got a point now that it for sure travels through. If we have the line will take the x coordinate. You can call them x sub zeros if you want. It will take the direction vector and it will mash them together. X coordinate, x component of the direction vector. That's how the lines work. Do you remember the equation of the lines? They look like this stuff, right? Where this is your point, x, y, z. This is your direction vector, x, y, z. It's how we made them. Tell me what the y would look like, please. Tell me what the y would look like.
T.
Why doesn't it have an actual constant up there? Why doesn't it have that?
0.
Because we have 0. So 0 plus AT. And Z, if you want to do that one, what's the Z start with? Come on, quickly, what's the Z start with? Plus or minus?
Plus 11.
It's pretty interesting. These planes are going to meet somewhere in space. Their meeting is going to be a line. I know that line because I did the system. It's going to travel through that point on the XZ plane. Using that point and the direction vector, which is mutually orthogonal to our normals, we now have an equation of that line. That's pretty cool. We just found out the line that these planes make. Pretty neato. Neato. Real neato. I don't care. What's it mean to me? It's pretty neat if you need to do this stuff on some other topics. We don't have time to cover all of them, but it's pretty interesting at least. That we can even do it is pretty cool, I think. So if you guys feel okay with the idea. Now is finally our time for distances. I love distances. Finally, we've been talking it up for a while. We're gonna figure out how to find the distance between a point in a plane, parallel planes, skew lines, and a point in a line. I'm gonna have to warp speed this stuff. I'd like to prove it to you, but I need your full cooperation if we're gonna do it. Okay, so it's gonna be just me talking for a while about proving this stuff. I'm gonna go very fast, and then I'll show you some examples. We'll do 2 of them, and that'll be our whole time. So we're going to find distances of the following things. We're going to start with distance between a point and a plane. Here's our idea. Pick a point away from, you have a point away from a plane. Somehow, we'll call it P1, find a point on the plane. Create a vector. You know what? If you don't want to write this down, I don't care. You don't need to write it down. This is just the proof behind it. Okay? You don't need to unless you want it for future. That's fine. But here's the plan. You're going to have a point that's off the plane and a point that's on the plane. If it's not directly perpendicular, what we're going to do is we're going to project it onto the normal. If it's not directly perpendicular, you can project it onto the normal. So this point 1, let's call it x1, y1, z1, and this point x0, y0, z0. If you remember this stuff, component projection, I'm just looking for distance, so I'm not worried about scalar, I'm not worried about vector projection, I'm worried about scalar projection or component projection. I just want to find a distance, man. Verify that this distance, the projection, is that distance. The same thing. Do you remember that formula at all? When we want to find the scalar projection of B onto A, we did B first, dot with A divided by magnitude of A, the one you're projecting on. So if I change this to this, if the component projection is the distance, all I gotta do is change the names of my vectors. The one that we're projecting is the B. The one we're projecting is the P0 to P1. We're projecting that onto the normal, and then dividing by the magnitude of the one we projected onto the normal. Now if we do that, this right here is that vector dotted with, if I give my normal our usual components ABC, if I give that to my normal, then this is vector P0 to P1, this is vector and the normal, this is the magnitude of vector and the normal. Head nod if you're okay on the proof so far. This is the cool part. If we you're going to miss it if you blink at it. It's pretty darn neat. If you dot product this, I'm going to do one more thing here in a second. I'm going to add some absolute values because we never want our distances to be negative. So I'm going to add some absolute values, but that's all that's going to do. So we go, okay, yeah, sure. Then we get, I'm going to do it kind of fancy-like. Here's what I'm going to do. Just watch carefully so I don't miss you. When I dot product, I'm going to multiply this times this, this times this, this times this, and add them, correct? Which means I can distribute this to both of these, this to both of these, this to both of these. Do you catch it? So I'm going to get A, X1, I'm going to get B, Y1, I'm going to get C, Z1, but then I'm going to get this stuff, this A, X sub 0, this B, Y sub 0, and this C, Z sub 0. Now here's the neat thing about this. All this stuff, all that stuff that we did before, we called that letter. Do you remember distributing it, combining it, adding it over? That was our D. This is all D. So if I continue, the distance between a point and a plane looks just like this. You go, fantastic. What's that? What's that even mean? Firstly, there are no variables here. There are no variables. I want you to look at it real carefully. Where do the A, the B, and the C come from? The normal. It comes from the plane. Same A, B, C. The X1, the Y1, and the Z1, that is your point off of the plane. That's your X1, Y1, Z1. So literally, all you gotta do, take the normal vector, put the numbers here. Take your X, Y, and Z coordinates, put the numbers here. Add them together, subtract the D, take the absolute value, divide by the magnitude of the normal vector. That's how you figure out how to find the distance between a point and the plane. Does that make sense to you? Okay. I want to try one. You know what? I'm sorry. Do you want to try one, or can I give you the other ones first? Can we do that?
Yeah, let's do that.
You want to try one? Do you care? Do you want more candy? If I hit you in the face, don't sue me.
Oh, no. I didn't see
Nice.
looking at me. But thank you.
You said yes.
Oh.
That's why it was a good throw. Right to you. You literally, she could have just, want to try that?
No.
Me neither. I don't want to hit you in the face. Now, there's something interesting that we're going to talk about here. What if that point were contained in another plane? Do you see the picture I'm trying to draw? The point's contained in another plane. What if that happens? Furthermore, what if the planes were parallel? Now, I'm not going to ask you, hey, find the distance between two planes if they're not parallel. You know why? Because there is none. Because they're going to meet. We just did that problem, intersection of two planes. It's a line. There is no distance. They actually cross. But if the planes are parallel, true or false? If the planes are parallel, they have the same normal vector.
True.
Yes. Okay, if the planes are parallel, they have the same normal vector, then when I move this when I move this over, we have the same normal vector. A lot of cool stuff happens. In fact, if we have that same normal vector, the distance between parallel planes, distance between parallel planes. If I give you two planes and they have the same normal vector, a lot of the things here, because you have the same A, B, and C, simplify out. They are gone. They're not going to be there anymore. What's going to happen is that we end up with only two different D's. Verify that's the only thing in planes that can possibly be different if they are parallel. If we have like AX plus CZ equals D, if we have that, I say, hey, here's two planes and they're parallel. Are these numbers the same for parallel planes?
Yes.
Are these numbers necessarily the same?
No.
It's the only thing that can possibly be different. And the only way that we get that different number is with that point. A different point gives us the different number. That's why that point in the normal vector define a plane. So if we have the same normal, the point is the only thing that's different. That point, when we distribute all of this this stuff here, that point, A, this, and this, that's what gives us the D. They're the same normal. All of this stuff disappears except the two D's. So if I want to find the distance between parallel planes, it ends up being this. You still have a normal, it's a common normal. It's still an absolute value, I want a positive. But the only problem, not problem, the great part about it, the only difference between the planes is the D's. Take the D's, subtract them, find the absolute value of that, divide by the magnitude. For instance, just so I can give you at least something. I'm glad I'm doing this one too, because it's useful. This is not good. This is, don't give me things like this, don't deal with things like this, don't let this be, this shall not pass. Right here, do you see the problem with if that? Someone didn't simplify their vector enough, and you should. So when you can divide everything by 2, like in this case, do it. True or false? Those are parallel. True?
If those are vectors, don't they both have the vector notation above the variable names?
These ones?
Yeah.
Those are planes.
Okay.
So not vectors, just planes. What is the joint, common, whatever you want to call that? What is the normal vector for this here?
2 negative 1.
Got my notation confused. That's the normal vector right there. They share the same normal vector. They have to, because they are parallel. They are parallel because they share the same normal vector. And now if you're okay with that one. As soon as you simplify this, you can find the distance between these parallel planes. And it's very, very fast and very, very easy. Just don't use that number. You have to use a simplified one. So as soon as you do it, this is the D, that's not the D. So we have our normal vector. We've got our, what's our D for the first plane? What's our D?
2.
2. What's our D for the second plane?
4.
That's the distance between those planes. Yeah, square root of 14. Are you guys okay with that one? Proved it, but I want to make sure you see where the numbers are coming from. If you have to find distance between planes and you know they're parallel, hey, take these two D's, subtract them, whatever order, doesn't matter. Absolute value says it doesn't matter. Subtract them, divide by the magnitude of the common vector and normal vector, and you're good to go. Head nod if you're okay with that one. I want to go back to this for just a second, just to prove it by an example. What if you didn't know they were parallel? freaking should, okay? But if you didn't know, then you'd find a point on this plane. So, do you have this down? Can I erase it? Remember 2 over root 14, okay? So let's say you didn't know. You go, if I don't know they're parallel, well, you should. But if you didn't, then you should check. But if you didn't, I'll find a point on it, because we'll be able to do it that way. To find a point on a plane, any point on the plane, you can set 2 variables equal to 0 and find out where it crosses an axis. Planes will cross the axis unless it's parallel to the axis. If it's parallel to the axis, you wouldn't have that variable. Anytime you have a variable, you have to cross that axis. This stuff should be ringing a bell. So if I set x equal to y equal to 0, I get 2z equals 8, or z equals 4. I get z equals 4. There's a point there. It's 0, 0, 4. That is a point on plane number 2. That is a point on plane number 2. It's actually the point where plane number 2 crosses the z-axis. That's what's going on. If I said, how far is this point from that plane? Here's how you do it. It's right here. So if you didn't know they were parallel, you have this as your Beckett plane. I want to show you so you see where it works. Here's our normal. We put 2, -3, 1, and 2. Here we put 0, 0, and 4. Do you see where those numbers are coming from? Okay, so, okay, now so by square root of 14, because I already did it. What is it again? 2 times 0. Plus?
Negative 3 times 1.
Plus?
1 times 4.
How much?
1 times 4.
Uh-huh. Do you see where the 1 times 4 is coming from?
Yep.
It's a minus. 0, 0.
2.
That's how you find the distance between any point in a plane. You literally plug in x, y, z coordinates and the x, y, z components of the normal vector, divide by the magnitude of the normal. That's all there is to it. Works out the same. Why? Because those planes were parallel. That's why. We got 2 more things to do, and then we're going to be done. We're so close, I want to wrap it up. I want to give you the idea for skew lines. Here's just the idea for skew lines. Distance between skew lines. Show me with your hands what skew lines look like. Can you do that? What do skew lines look like? Yeah, don't throw gang signs at me, okay? Skew lines don't meet in space, but they're not parallel. So here's the idea. If lines are skew, they have to be contained by planes which are parallel. You have to be able to find parallel planes which contain those skew lines. Did you catch that? There's an infinite number of planes that can contain a line. You have one line, there's billions of planes that can contain that. But as soon as I have another skew line, I pick one here and one here that are parallel. Does that make sense to you? I do that. Okay, so the idea is define those parallel planes, then use that. Distance between parallel planes. How we can, and that'll be the shortest distance. So how we can do that, lines have direction vectors. So what you would do first, you'd find the direction vectors of your lines. If those direction vectors are in planes that are parallel, they will have a common normal. You find the normal between those vectors. That will be the normal of the plane. Every line is given, we've had some lines up here, I don't have them right now, but every line is given to you with at least 1 point, correct? You just plug in t equals 0, you get a point. Lines have points. 2 lines, 2 points. I know it's a lot at one time. If you've got lines like this, they get direction vectors like this, consider them to be contained in parallel planes. Planes need a normal. Cross them to find your normal. Now you have a normal for both planes. Lines have points. Take the normal with each independent point, find the equation of the planes. Two of them. Those planes will be parallel. They have the same normal. They can't be anything other than parallel. So when you find those 2 planes that are parallel, you have the equation, right? Those equations are going to have some d's in them. Take the d's, take the common normal, distance between parallel planes. So after this stuff, distance between parallel planes. That's the idea on how you would do it. The last thing that we're going to do how to find the distance between a line and a point. Doesn't seem so hard, but consider that the line's going through space. And you go, how would I do that? Here's the idea. If that's our line, number one thing I want to do, I want to put a point on the line. We'll call it Q. I want to find a vector. I don't know where that point's going to be, and I can't just say it's right under P because I don't know where that's at. So I need to put some point on the line, and the point's typically given on the equation of a line, right? It's given to you. And I have a point P out here on space off of the line. Create a vector from Q to P. Let's call that U. And I want to find this. Keep in mind there's going to be an angle between any vector off of the line and the vector of the line itself. Let me go through it real quick. We'll do our example, okay? So check it out. I get a point not on the line. If it's not on the line, I can find a point on the line, Q, and a vector 2P. Head down if you're okay with that one. Lines also have vectors. Any 2 non-parallel vectors have an angle between them. If you use sine, this distance is, let's see, sine would be opposite over hypotenuse. So if I solve for this, it's going to be hypotenuse sine theta. You guys okay with that? Here's some math magic. We're gonna invent some stuff. Right now what I'm going to do is I'm going to multiply both sides by the magnitude of vector v. Magnitude are scalars, right? So I can multiply both sides by this scalar and still consider it to be equal. And you go, what, Leonard, you're crazy, man. You got too much candy. I have had some candy today, which is why I'm talking very fast. But that's okay. I don't get it very often. So what? Why would we do it? if you look at that, that should be really, really, really familiar.
Yeah.
Not just the cross product. Very close. The magnitude of the cross product. The cross product has to, this is not a vector. This is a number. So it cannot be a vector. So it can't be the cross product, but it's the magnitude of the cross product. If I divide both sides by the magnitude of v, the distance between a line and a point is there. I would like to give you an example since this recording device is going to stop in 4 minutes. So we're going to stop in 4 minutes. Here's the things we need. We need a vector from P to Q. We need a vector from the line to this point. This point Q would be -2, 1, -3. I know I'm moving fast, but can you follow me on the point from that line? It's pretty easy to find a point on a line. It's with symmetric, it's just negative, positive, negative. We get 2, 1, 3. We also need a vector. The vector is really easy. I love vectors from that form of a line. You just read the denominator, that's the vector. We also need a vector from Q to P, or P to Q, doesn't matter. Yep, that'll work. And then we can find our distance. Our distance is simply U cross V magnitude divided by magnitude of V. This V. There's one thing I want you to not do though. It's probably the most important thing. I told you this. I said, you can manipulate vectors as long as you want, blah, 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 but you can't do it unless they are talking about distance. Even though you really want to, don't mess with that. Don't divide by -3, don't factor anything out, you have to leave that. I gotta give you just the answers. If you cross U and V, so you cross these two things, you're going to get, 12i minus 12j minus 12k. If we take the magnitude, the distance is 6 root 42 over 7. The magnitude of v is the square root of 14. So this is your answer. I want you to try it. It's not that hard of a thing to do. We just take a point, we take a line. This line gives us a point. It gives us a vector. Just find the vector between these two guys, cross product, magnitude, and divide by the magnitude of that vector, the one from the line, and that does it.